become more intellectual, responsible, competitive, and yes, academically enhanced.
Amity has been a great learning process for me. My future prospects, my dreams, and when I came here, I thought that it will be the best place that can fulfill my dreams.
Hi all, I am Joy Sahaya Varshini, pursuing Masters in Urban and Regional Planning from Amity University. I started painting and sketching at the age of 9 and it has developed into one of my favorite hobbies. The confidence that Amity has developed in me has contributed towards my interest in rapid sketching.
A very good morning and welcome all to the second day of International Workshop on Recent Trend in Applied Mathematics for Engineering and Technology, organized by Department of Applied Mathematics, MIT University, Madhya Pradesh. Today, our first speaker is Dr. Rajat Tripathi. Before his talk, it's my pleasure to introduce him. Dr. Rajat Tripathi is currently working as an assistant professor at National Institute of Technology, Jamshedpur. He has done his PhD from IIT Dhanbad. His research areas are fluid dynamics, heat and mass transfer, and non-fluid flow. He has published several research articles in different international journals of repute. He is an active reviewer for various SCI journals like the Journal of Applied Mathematics, International Journal of Applied Physics, and Cognate Engineering. He has also delivered several talks at various national and international events. Now, I would like to invite Dr. Tripathi to share his insightful knowledge on the topic mathematical analysis of airflow cooling in modern data centers. Please, sir.
Thank you. Thank you, ma'am. First of all, I would like to thank the organizers from Amity University, Madhya Pradesh, for inviting me to deliver this lecture. I am thankful to Dr. Ram Kumar, Dr. Avnish Vaishwar, and Dr. Rajat Vash, and all the others who are organizing this workshop and have invited me to deliver a lecture in this workshop. So to begin the session, I would like to just point out a correction. The title of my talk that I gave to Dr. Ram, I think there is some problem. I think there is some communication gap. Actually, the title of my talk is a little bit different. So I'm going to share my screen, share my slide with you all. Okay, so title of my talk is Artificial Intelligence Meets Fluid Dynamics, a new paradigm shift in fluid dynamics. So to begin with, at the outset, I would like to just inform the audience about the title and about this talk. So as the title suggests, Artificial Intelligence Meets Fluid Dynamics. I have been a researcher who is working in the field of fluid dynamics for last 10 years. And recently, you all are aware that artificial intelligence is taking the world by storm. A lot of development has happened over the past few years in artificial intelligence, and there was a need to integrate this artificial intelligence into the research in fluid dynamics. So my talk is specifically structured in that manner, that how we incorporate artificial intelligence into fluid dynamics so that we can understand the fluid processes, fluid flows in a better way. So just a second. Okay, so this is the outline of my talk. First, I'll discuss some basic introduction about machine learning, artificial intelligence, where I'll discuss the structures of artificial neural networks. And then building upon that, I will discuss the very specific kind of neural network known as physics-informed neural network. And then I'll illustrate one problem of how physics-informed neural network or machine learning or artificial intelligence can be used to solve the problems arising in fluid flows. and then building on that, I'll discuss an actual problem that we have solved using machine learning, using artificial neural networks, and then I'll conclude my talk. So to begin the session, I would just like to point out what machine learning is. Most of you may already be familiar with the concept of machine learning. Machine learning, as the name suggests, it is the learning of machines. That how machines learn from different kind of things, and it is very similar to how we humans learn different kind of things. Like when we were kids, and our parents our parents tried to teach us about different kinds of structures. Like when you see a circle at this point, you will immediately say that it is a circle. When you see a photo of a quadrilateral, you will immediately say that it is a quadrilateral. But it hasn't happened that we don't actually realize it the way it has happened, but we are in a way trained to identify these kind of images. So when we were kids, our teachers used to show the pictures of circle and say that it is a circle. And it got registered into our minds, and therefore now we can easily identify what a circle is. And the same thing goes for every other thing. Like if you see a picture of cat, you eventually say that it is a picture of cat. It is not a picture of dog, because we have been seeing it. Our mind has learned it by seeing different kinds of cat, and we can immediately say when we see a picture of cat, right? So what happens is, when you see something, what happens is there are neurons in our brain which gets fired, and the image or the information there is registered in our mind. Our mind is trained in that way. Okay, so that's how machines have also been made to learn things use by looking at different functionalities of brain. So one of the key concepts in machine learning is artificial neural network. So as you can see that on my left, there is something called neuron at one end and synapse at the other end, and in between there is axon. You can see dendrites, and on the right hand side there is a mathematical function kind of thing. So I'll just start with the analogy between the actual neuron synapse and the artificial neural network. So when we see something or when we feel something, then what happens is neurons in our brains are activated. The information is actually received at neurons, and if we feel that it is something that has to be processed, then it is passed on to the axon terminal, and we immediately give an output. For example, let's say there is a mosquito sitting on my hand, and as far as it is not sucking blood from our body, or it is not pinching us, we won't feel it. Let's say we are not looking at our hand, we are looking at somewhere else, and there is a mosquito sitting at my hand. So we won't feel it, it will stay like that. But as soon as it starts sucking blood from our body, or we will immediately feel a pinch, and then this information is passed through neurons. Neurons get fired, and then immediately what we do is we try to shoo it away, or we try to send it away with different actions, right? So that is how neural networks have also been built. When you receive an information, then neural network, it tries to see if it is a useful information or not. If it determines that it is a useful information, there is an activation of the neuron, and then this neuron is fired to produce an output. So there is this analogy between the actual working of neural system in our body and the artificial neural network. Because it is artificially been built, therefore we call it artificial neural network. It so happens that when you receive an information, then this information is processed. Like I explained the idea of mosquito biting us. So when mosquito bites us, that information is processed in our brain, and then brain or our body takes the action as it is suggested by the brain. So we either try to shoo it away, or we try different methods of sending it away. In the same way, in the neural network, when you receive an input, what happens is we get the input, we try to process it through some different layers, extract useful information from it, and then we pass it on to the output. Okay. So that is how artificial neural networks work. Okay, so before going into the other details of how artificial neural networks or artificial intelligence is integrated into the fluid dynamics problems, I'll just use the whiteboard to explain few basic concepts here. So is this white screen visible to all?
Yes, sir, visual.
Okay, so as I explained, when you have a neural network, artificial neural network, so what we have certain sets of inputs. These inputs, let's say these are inputs. These are then passed on to different layers. Let's say there is this layer and there is this layer. So in total, in an artificial network, we have 3 layers. The first layer is known as an input layer. The second layer or the middle layer is known as the hidden layer. And the last layer is known as the output layer. So what happens is when you receive some input, it is passed on to the hidden layer where all the processing happens. So what happens is all the input neurons are actually connected to all the neurons in the hidden layer. All the in between neurons are also connected to all the other in between neurons in this manner. And then this output from the hidden layer is connected to the output layer. And then from there we receive information. Or we get an output. Okay, so these circles that I have drawn here, these are known as neurons. The edges with which these circles are connected, these are known as weights. All the edges, these are known as weights. From neurons, from one neuron to another neuron, the neurons are connected through different weights. Okay, so this is an input layer, hidden layer, and output layer. When you receive an input, when machine receives an input, it sends it for processing. The processing happens in the hidden layer and then it is passed on to the output layer. Okay, this is an example of a little complicated neural network. If I have to draw a simple, let's say, neural network with only one hidden layer and let's say 2 inputs, input 1 and input 2, and let's say there is only one hidden layer. So inputs are connected to hidden layer, the neurons in the hidden layer, and there is only one output. And these neurons in the hidden layer is also connected to the neuron in the output. Let's say you are getting an output here. Okay. So what has happened up until now is we have solved the fluid dynamics problems, which are kind of ordinary or partial differential equation with some initial and boundary conditions via different numerical methods, and have used those numerical solutions to process them into the neural network to find different information. Okay, so let's say you have a simple differential equation. Let's say d2y by dx2 plus let's say a dy by dx plus by equal to let's say some function f. So we all know how to solve this problem. And once you solve it, because it is a second order ordinary differential equation, so in order to fully solve it, you need 2 conditions. Let's say you are given ya equal to some y1 and yb equal to some y2. So this is a full system. This is a complete system. If we assume that A and B are, let's say, functions which are continuous, and F is also a function which is continuous, then we can find its analytical solution. We can find its complete solution. Now, what happens is, then once you find its complete solution, for different values of X, you can find different values of Y, right? So what has happened in the past few years is we have used artificial neural network or machine learning to learn about the input and the features hidden in the input, right? When we supply it some input, what output we are getting, and how do we make sense of that output. In the recent past, what has happened is, in recent 3-4 years, that neural networks are used to solve are now being used to solve the differential equation or this kind of problem. Because it is a simple linear differential equation, we can find its analytical solution. But if I make it non-linear, let's say d2y by dx2 into dy by dx plus, let's say, ay square equal to b and some xy. Then, because this was a linear system, this was a linear differential equation, it was easy to find its exact solution. But now this is a non-linear differential equation. Finding its exact solution is not easy. So what people used to do is, let's say we are also supplying boundary conditions y equal to y1 and yb equal to y2. Now, because it is a non-linear differential equation, it is very hard to find its analytical solution. Right. So what people used to do is they develop different numerical schemes to find the solution of such kind of problems. Like there is finite difference method, finite element method, finite volume method, which are used to find the solution of this kind of problem. And in all those numerical schemes, what happens is, let's say our domain of X is from A to B. Let's say the interval in which this differential equation has to be solved is between A and B. So what used to happen is, either we use finite difference method, finite element method, or finite volume method. We discretized its domain into smaller intervals, and we used to find solution at these different points. So that is how the numerical methods work. And once you solve this problem, you can find the value of y at a given value of x. And once you find this, then neural networks were used to analyze the solution. Now the things have changed. Now, in order to solve this system, in order to find the solution of this system of differences, this differential equation with some boundary condition, we do not need numerical methods to find the solution. In fact, we can directly use the neural networks to find its solution. So if we combine the two things that I just explained here, earlier we used to have numerical schemes for solving a system, for solving an initial boundary value problem. Once you find the solution, then the solution was supplied to neural networks to analyze the hidden features in the differential equation or the problem. So numerical schemes were used to find the solution. Solution was supplied to neural networks to extract the features. Now, what has started happening is, now we can use neural networks directly to find the solution of differential equation, to find the solution of such kind of problems. And then once the solution is found, we can use it in a different neural networks to learn about the solution. So we are actually moving towards full automation. That is, the solution is also found using the concept of machine learning or artificial neural networks. And then the machine is also learning from the solutions to inform you about the features of the solution. So this thing, that solving a differential equation or initial boundary value problems using neural network is known as physics-informed neural network. And that is what I am going to discuss here. Okay, so this is a basic structure of physics-informed neural network, where we have, as I said, any neural network has three layers: input layer, hidden layer, and output layer. there is an additional layer in physics informed neural network. So let me explain you how it works. So let's say you have two inputs, X and Y. These inputs are fed to the hidden layer, right? These are the hidden layers. These are the neurons in the hidden layer. Once these input are fed to the neurons in the hidden layer, all the processing happens here, and then the output of hidden layer is processed to the output of it goes into the output layer where you learn about the solution. But how do we solve differential equation using this kind of structure? So that is where the beauty of this method comes into existence. That is what the beauty of this method is. So what we do in physics informed neural network is we convert the initial boundary value problems or partial differential equation or ordinary differential equation into an optimization problem. So what physics informed neural network has done is, just a minute, physics informed neural networks. What it has done is it has started converting the problems of ODE or PDE into optimization problems. So let me explain how the neural networks are used to convert the problems of ODE into optimization problem. So I'll explain it with a very simple example. Let's say we have this same ODE problem that we had, d2y by dx2 plus a dy by dx plus by is equal to fx. Okay. And there are conditions ya equal to, let's say, y1 and yb equal to y2. So now we are going to convert this problem into an optimization problem. Okay. So let's see how it is done. So what happens is, as I showed you the structure of Yes, as I showed you the structure of physics informed neural network, you see there is an input layer, there is a hidden layer, and there is an output layer. Okay. And the the neurons, the circles that you are seeing, these are connected. Different neurons are connected via different weights, and these weights are nothing but functions of X or functions of Y or functions of X and Y. Okay, so let's see how this problem is converted into an optimization problem. So let's say you have, because X is between A and B, the interval in which you want to find the solution. So what happens is we find different points between A and B, not necessarily equidistance. You can take any number of points in it. You can take only 5 number of points, or you can take 10 number of points, or 100 number of points between A and B, not necessarily equidistance. Whatever point whatever point you want, you can choose between A and B. So let's say I am choosing x1, x2, all the way to xn number of points between A and B. Okay. So as I said, let's say I have a simple, because input here can only be an X. So there is one input. And let's say it is going into 2 neurons in the hidden layer. Okay. Let's say this is going via weight 1 and weight 2 in the hidden layer. And these are going again back into the output via weights, let's say W3 and W4. Okay. Okay. Or to make it more simple, to make it simpler, let's say I have one input and there is two hidden layers. There is a hidden layer, two hidden layers, and from this hidden layer we are getting one output. Okay. Let's say this is weight 1, weight 2, and this is weight 3. Okay. We can have all the any kind of neural network that I can find. Okay, that I can create. So our aim is to solve this problem. And as I said, I'll convert this into an optimization problem. Okay. So there is one input. There are two neurons in the hidden layer and there is one output. Okay. This is your hidden layer. Okay. So hidden layers, as I said, these are connected via different weights, and these weights are nothing but functions or constants. You can choose them as functions or constants. Okay. So because there is only one input, so let's say it is a function of single variable x, not fx because we have already used it. Let's say it is a function gx. Weights are some function gx. For different weights, you can consider different functions, g1x, g2x, g3x, or you can consider them as same functions. So let's say we are considering w1, w2, w3, w4 as different functions, g1, g2, g3, g4x. You can have them as same functions also. Okay. So when you provide an input, let's say single input xi, it goes to two different neurons in the hidden layer via weights W1 and W2, which are actually functions of X. Okay. And then let's say there is one more layer in the hidden layer where it goes to W3, W4, and then this information is recorded as an output via weights W5 and W6. So when you give an input X, the output in the second neuron is actually x1 into w1, the product of input with the weight. The output here in the second neuron is w2 into x1. The output here is this is then considered as some other function which is known as activation function, or you can directly supply it to here. The output here will be x1 w1 into w3, and output here will be w2 x1 into w4. In the same way, we can take this as input to this neuron and we can find it here. So because all these weights w1, w2, w3, w4, w5, w6 are all functions of x, right? So for a given value of x, you can find it. So this output is also going to be a function of x, right? Because everything is a function of x. It means when you give this neural network an input x, it produces an output hx. Fine. When you give it an input x, it produces an output hx. Now, as I said, I am discretizing my domain AB into, let's say, n number of points, x1, x2, all the way to xn. Okay. So for different values of x's, I can find different values of hx, right? Given that w1, w2, all the weights are already prescribed. So for different values of x's, I can find the value of output. And let's say that, let's impose that this hx is my solution of this problem that we were trying to solve. So because now we are trying to solve this problem and we have created a neural network which has no relation with the above mentioned differential equation or problem. So you might say that this is an absurdity. This can never be solution of that problem, because this neural network up until this point has no connection with this differential equation. There is no connection that we have established between this differential equation, this boundary value problem, and this neural network. So how can we assume this to be my solution? That is where this problem of converting ODE or PDE into optimization problem is coming into picture. Okay. So because we are assuming it as my solution, it means this must satisfy the given differential equation. It means Hx must satisfy the given differential equation and boundary conditions. Right. It means this Hx must satisfy this differential equation, and it also must satisfy these two boundary conditions. But as of now, we have established no connection between the boundary value problem and the neural network. So this is actually not true. This is, at the first instance, it is surely not true. So how do we improve it? So in order to improve it, we are going to convert it into a different problem. So consider this system and another system where I have, consider this new problem. D2, let's say some y cap by dx2 plus a dy cap by dx plus by cap minus fx equal to 0. That we have actually written the same thing in a different way. D2 y cap by dx2 plus a dy by dx plus by minus fx equal to 0, along with y at a minus y1 equal to 0 and y at b minus y2 equal to 0. Right? This is actually the same problem, not a different problem. Okay. But if I am assuming that this Hx is my solution, if I am assuming that this Hx is my solution, this must satisfy this differential equation and the boundary conditions, right? And how did we find Hx? By creating a neural network, supplying an input x, defining different weights at some functions of x, and we were getting Hx, right? So if this Hx is my solution, it means we can replace this y cap by h, and we can write d2h by dx2 plus a dh by dx plus ph minus fx equal to 0, given that h at a minus y1 must be 0 and h at b minus y2 must be equal to 0. Right? But at this point, it is not going to happen. It is certainly not going to be 0. This is certainly not going to be 0 because at this point, h is not my solution because it has not been incorporated into the differential equation. There is no relation between h, this neural network, and the differential equation. So what we do again is, let me again draw the neural network. There is this input x. It goes to two different neurons in the hidden layer, which again go to two different neurons in the hidden layer, and then an output is produced. This is your input, output H. Okay, so in order to make sure that this H is my solution, what we do is we calculate dH by dx and d2h by dx2. Now, how that happens? Because these are merely weights W1, W2, W3, W4, W5, W6, which are all functions of x. So if you want to compute dH by dx, we can use the chain rule of differentiation. We can find it as dH by dW6 into dW6 by dW4 into dW4 by dW2 into dW2 by dx, right? Following this path, because W2 is connected to W4, W4 is connected to W6, which is connected to H. So what we can do is, we can, in order to find dH by dx, I can do a back propagation. This is known as back propagation. To find dH by dx, right? In the same way, I can find d2h by dx2 also. Okay, using, once you have found dH by dx, this can be found as d by dx of dH by dx, right? So we can again actually do the back propagation via this or this to find out the value of d2h by dx2. Because when you supply in input x, it is giving you an output h, a function of x, because all these are functions of x. So in fact, we can do this kind of differentiation here, right? Okay, so in this way, we can from x and from hx, I can find dh by dx and d2h by dx2. Okay, once this is found, now you see that because I assumed that this h is my solution, so it must satisfy the given differential equation and this thing. It means when you plug h into the differential equation, it must be equal to 0, and this must also be satisfied. But at the first instance, it is not going to be equal to 0, and it is not going to be equal to 0. It means you need to make certain adjustment in neural network so that this becomes 0. Okay. So what happens is now dh by dx, because you are calculating dh by dx, d2h by dx2, and you see that there is chain rule of differentiation involved here. So what we do is when we calculate dh by dx, d2h by dx2, because these all the weights are known to us. Okay, so we can find dh by dx and d2h by dx2 for any given input. Okay, so when we calculate it, once the h is found, you plug that h in the differential equation, and if the output is not equal to 0, it means we need to make certain adjustment. The adjustment that we make is we change these weights W1, W2, W3, W4, W5, W6. Okay. So you found H at the first instance, and you see that it is not satisfying the given ordinary or partial differential equation. It is not satisfying the boundary condition. So what we do, we calculate dh by dx, d2h by dx2, because for this to be 0, you need to find d2h by dx2 and dh by dx. Okay. Once you calculate and you see that it is not equal to 0, what we do is we change these weights. We adjust the weights, and we keep on doing it until this becomes 0. Okay. You found dh by dx, d2 by dx2. You supply it to your differential equation and see if d2h by dx2 plus a dh by dx plus some dh minus f, if it is equal to 0. If it is not equal to 0, we change these weights. Once you change these weights, it means you have to again perform this dh by dx and d2h by dx2, because now the weights have changed. Okay. For a given initial set of weights, you can find dh by dx and d2h by dx2. Once you find h, dh by dx and d2h by dx2, you supply all those things here and see if it is equal to 0. If it is not equal to 0, it means you have to adjust your weights. It means you need to change W1, W2, W3, W4, W5, W6, which were initially defined as functions G1, G2, G3, G4, and so on. Okay. So if it is not coming equal to 0, you change the weights. And once you change the weights, you again have to calculate dh by dx and d2h by dx2. Because you see that h is connected to x via weights W2, W4, W6. So once you change W2, W4, W6, you have to calculate dh by dx and d2h by dx2 again. Okay. So let's say at the first instant, this was not equal to 0. You change the weights W1, W2, W3, and so on, and you again found h, dh by dx and d2h by dx2, and then you are again supplying it to your system and looking whether this is equal to 0. If it is again not equal to 0, you again go back, change the weights, and calculate h, dh by dx, d2h by dx2, and see whether when supplied to the differential equation, it is becoming 0. If it is again not becoming 0, you again go back and change the weights. So it looks like a lot of work, but when you use a computer program, when you write a computer program, it is actually not that difficult. In fact, in the Python language, there is this already built-in code gradient, which finds the derivatives, not just the ordinary derivative, but partial derivatives also. So when the changing of weights and finding dh by dx and d2h by dx2 is not that difficult a task when you use it in a computer program. But the underlying concept is this. You keep on changing the weight until this becomes 0. But at this point, I have not said how this becomes how has this become an optimization problem. So for that, let me open another blank slide. Okay. Is this blank slide visible?
Yes, sir,
Yes,
it's
sir,
visible.
visible.
Okay. Okay. So up until this point, we have tried to find the solution of not OD, boundary value problem. And as I said, I'm going to convert into an optimization problem. Okay. So let me again write the system, the OD and the boundary conditions. With conditions YA equal to Y1 and YB equal to Y2. Okay. As I said, my X is lying between A and B. And let's say I can find different points between A and B, not necessarily equidistant, any point between A and B, right? Let's say if A is 0 and B is 1, then your intermediate points X1, X2, these can be 0.1, X2 can be 0.15, X3 can be your 0.7, X4 can be 0.95 and so on. Okay, you can take equidistant point or non-equidistant point, it doesn't matter. So when you supply this corresponding to this boundary value problem, when you create a neural network, you supply these different inputs x1, x2, xn. Okay, let's say this is your x from xi from I equal to 1 to n. When you are supplying it to a neural network, it is giving you an output. Let's say output is hxi. For n number of different inputs, you can find n number of different h's. Okay. And as I explained, once h is found, you can find dh by dx and d2h by dx2 using back propagation. Okay, using back propagation, we can find dh by dx and d2h by dx2. Okay, once these are found, you put the values of h, dh by dx and d2h by dx here, assuming that h is your solution. If h is your solution, use this h, dh by dx, d2h by dx2 in here to see if it is satisfying the given problem. If it is not, we keep on changing the weights. Okay. So at the first instance, what we do is for different inputs, xi for I equal to 1 to n, for I equal to 1 to n, we generate the data set hxi. These are n number of outputs of the neural network. Okay. Once these n number of neural networks are obtained, we create a loss function. We create something called loss function, which is actually modulus of d2h by dx2 plus a dh by dx plus b h at xi minus f at xi. We create this loss function. Okay, we create this loss function and we take the least square in the least square. Okay, so let's say there are n number of points between A and B. So we take the mean square error. Okay, so for n number of inputs from a neural network, we are finding n number of outputs. from these n number of outputs, I am creating this loss function. Modulus of d2h by dx2 plus a dh by dx plus bh minus f whole square divided by n. That is, we are calculating actually mean square error from the number of outputs and from the dh by dx and d2h by dx2. And now, if we can minimize this mean square error, if we can minimize this mean square error, it means the value of h, if we can find through neural networks for which this error is minimum, that must be the solution of our differential equation. Understood? Right? Because our problem is d2y by dx2 plus a dy by dx plus by equal to fx. And if we assume that h is our solution, then you must have h satisfying this differential equation. It means if you find the loss function in this manner, that 1 upon n modulus of d2h by dx2 plus a dh by dx plus b h xi minus f at xi square. If this function is minimized, then the corresponding h is our solution, because if h is solution, it must satisfy this one. And because we are actually find the approximate solution, so ideally this should be 0. But because we are finding the approximate solution, this is not going to be 0. But if you can keep it to, let's say, 10 to the power, this error function is 10 to the power minus 8 or 10 to the power minus 10, then that is a very good approximation to your solution, right? So in this way, the problem of solving an ordinary differential equation has been converted into an optimization problem where you want to minimize this loss function. Okay, and you see that up until this point, the boundary conditions have not been incorporated. The boundary conditions were ya equal to y1 and yp equal to y2, and they have not been incorporated into it. So in order to incorporate them, we create a big loss function, which is actually this one, d2 hxi by dx2 plus a dhxi by dx plus b hxi minus fxi whole square. You also create the loss functions for these boundaries. Y at a minus y1 or h at a minus y1 square plus h at b minus y2 square. Now, if you can minimize this whole thing, the value of h that you will get from the neural network, that will be your solution of the differential equation, solution of the boundary value problem associated with this differential equation. So in that way, the solution for the finding solution of the boundary value problem has now been converted into solving an optimization problem. This can be solved by various heuristic optimization procedures, such as particle swarm optimization or genetic algorithm and so on, ant bee colony method. There are various inbuilt optimizers which can be used to solve this optimization problem. So that is the basic idea of physics informed neural network. This whole process is known as physics informed neural network. Why this name? Because in the neural network, you are incorporating the physics of the problem via derivatives. You all know that derivatives are nothing but quantities of physics. These are actually physical things getting incorporated into the neural networks. So that's why we call it physics informed neural network. And it is only it only came into existence in 2019. So this is a fairly recent development in the field of neural networks. Okay. So I'm going to now my share slides. So this is the architecture of physics informed neural network. When you give an input, the input is processed through the hidden layer via different weights. There are, you see that different layers in the hidden layer, two layers in the hidden layer. The layer one contains three neurons and the layer two contains four neurons. These are interconnected. And then the output of the hidden layer is fed to the input layer. Okay. So it means for the inputs X and Y, you are finding output Y, U. Okay. Now from this, we can use the back propagation to find the all kinds of derivatives of U. If U is function of two variables, two inputs X and Y, then you can find del by del X, del by del Y, del 2 by del X square, del 2 by del X Y, del Y, and del 2 by del Y square. Okay. So this is how physics informed neural network works. And then we convert the problem into an optimization problem. So for an illustration, I just explained the example of an ODE. We can consider a initial boundary value problem with PDEs also. So this is a very well-known partial differential equation known as heat equation with two boundary conditions given at 0 and L and an initial condition given at t equal to 0. So using the physics informed neural network, I can create different loss functions. Okay. So these are the outputs of, because you see that U is function of X and T. So the inputs that I have X and Y here, you can also write it as X and T. For different X and T, the weights, the different weights, the edges that you are seeing here, these are also functions of X and T. And it means you, for given value of X and T, you can calculate weights. It means you can calculate U, which is also going to be a function of X and T. Once U is found, you can find all sorts of derivatives, partial derivatives of U, and then we can create the loss function. Okay. So for the heat equation problem, that is equation 1, the loss function is denoted here as LPD. What is NPD? NPD is the number of points that you are taking in order to find the solution, number of random points that you are taking. Okay. So what we do is, because it is a two-dimensional problem, there is this x-axis and there is this t-axis. So let's say this is our domain. So what we do is we find different points in the tx plane. So you see that each of these points are going to correspond to some value of xi and some value of ti. Okay. So let's say there are n number of points in the domain of the problem. Okay. So for different n values of xi and ti, I can create this kind of neural network. Once this kind of neural network is calculated, for those xi and ti, I can find the value of u. Now, up until this point, the neural network has no connection with the partial differential equation or the initial value problem or the boundary value problem. Up until this point, there is no connection. The connection is established by calculating the derivatives of u, partial derivatives of u, and in doing so, we keep on changing the weights up until that point where the loss function is minimum. Okay. So this is the loss function for PDE and this is the loss function for the boundary points. You see that this one is the loss function for your initial condition and these two are the loss function for your boundary conditions, because the boundaries are equal to 0. And at t equal to 0, it is xl minus x. So in that way, if you can minimize this error, it means the corresponding u is the solution of the problem. If you can minimize this one and this one, That is, if your total loss function is LPD plus LBC, that this one is LPD and this one is LBC, then if you can minimize this loss function, then the corresponding value of U for this has been minimized is your solution of the problem. Okay, so this is a almost brand new, you can say, because this was given by given by a researcher from United States, University of Colorado, Risey. So this is fairly new and a lot of research is still going on. Okay, so this is the idea of physics-informed neural network. Now, I'll show you an example where my research group has used this method to find solution of an actual problem. Okay, so we were actually working on a problem of understanding the blood flow in variable gravity. You see that when astronauts leave the Earth and go into the outer space, their blood flow is affected by the change in the gravity. So we have tried to capture the effect of variable gravity on the blood flow using this deep learning method known as physics informed neural network. Okay, so this is actually rotating frame of reference where we have calculated the effect of acceleration due to gravity when the angles are changed. So if your plane or if your spaceship is rotated with horizontal by an angle alpha, and with the vertical, if it is rotated by an angle beta, it means if your original frame is this green one and the rotated frame is this blue one, where the angle from the horizontal and vertical are alpha and beta, then the component of gravity in the this direction and this direction are evaluated by this. We all know how the rotation matrices work, right? When you rotate a vector, how the rotation matrix appears. So using that, we have calculated the the components of G in the two directions. Okay, in the R direction and in the Z directions, and then we have derived this partial differential equation to understand the flow of blood. Okay, I won't go into a lot of details of how this partial differential equation has arisen, but we have derived it. And once it is derived, these are the boundary conditions. You see that the domain is kind of cylindrical. So the boundary conditions, initial and boundary conditions, are imposed at the boundary. And once these are imposed, we have non-dimensionalized it, and then, as I said, created because let's say this is our domain of X, Z, and T. Okay, T and Z, T, Z, R, because the geometry is given in the RZ dimension, and T is the time variable. So we have this plane, and the blue points that you are seeing, these are actually the test points at which the output of neural network is calculated. These are known as collocation points. So these blue points in the domain are test points, random test points, not necessarily equidistant, random test point at which the output of neural network is calculated. And you also see that the boundary is also discretized. So we have that also. And once this is done, we have created this physics informed neural network and this loss function for PD. Okay, so if you look at the loss function of this PD carefully, you will see that it actually incorporates all the three partial differential equation into one big loss function. Okay, let me show you that. Okay, so this is your final equation, the continuity equation, momentum equation, and the momentum equation in the R direction and momentum equation along Z direction. So you see that this one is equal to 0 minus del P by del R plus this equal to 0, and this thing. So if you look at the loss function, then you see that this first term is actually your loss function of the continuity equation, because on the right hand side of continuity equation there was 0, so we only have this mean square error of the continuity function. Then this second term actually captures the momentum equation in the r direction. The second equation captures the momentum equation in the r direction because the right hand side of that also is 0, right? So that is your loss function for momentum equation. And when we create the loss function for momentum equation in the z direction, then you will see that this thing gets on the other side, and we have taken this last term as our loss function for the third equation, the momentum equation in the z direction. So in this way, all the three equations have been integrated into one big loss function LPDE. Okay. And these are the loss functions for Dirichlet boundary condition and Newman boundary condition. If you look at the boundary conditions here, then you see that these are Newman boundary conditions. And these are the Dirichlet boundary condition. Okay, so there is a big loss function for Dirichlet boundary condition, and there is a big loss function for Newman boundary condition, and they all have been incorporated. This is the loss function for Dirichlet boundary condition, loss function for Newman boundary condition, and this is loss function for PD. And they have all been incorporated into a big loss function consisting of loss function for the PD, the Dirichlet boundary condition, and Newman boundary condition. And now our problem of solving the blood flow in the variable gravity has been converted into an optimization problem, right? So if you can find via neural network, via physics informed neural network, because the variables inputs are R, Z, and T. So if you can find from any set of R, Z, and T, any randomly selected R, Z, T, you can find U, R, U, Z, and right, this is pressure. Then we can actually find all their derivatives. And if you can find such a function U such that the loss function here is minimum, that is of about 10 to the power minus 8 or 10 to the power minus 7, then it means that is your approximate solution, a very good approximate solution. And then you can plot it to understand the result. So we have actually solved it. And these are the results obtained by using the physics informed neural network for the velocities used at the inlet and outlet. Okay. Which is plotted against the radial coordinate r. So you see that this kind of neural network, this kind of method, it is actually a very big development as far as the fluid dynamics problems are concerned, because now you don't need to have different kinds of numerical methods like finite element method and finite volume method or finite difference method, because using finite element method or finite difference method, it is a bit difficult and it is not so straightforward for different problems. For different kinds of problems, for different kinds of geometry, you have to go for your different finite element method or finite difference method, because they all are geometry dependent. So when your geometry is, let's say, straightforward like this, then you can create easy meshes, simple meshes. You can find the solution at these points, and you can find your overall solution by finite element or finite difference method, right? But if your geometry is not that easy, if your geometry is, let's say, complicated, then finding the discretization at the edges or other things is difficult. If you use finite element method, then finding a proper element at edges is difficult. You have to find a proper mesh for it, and edges, it is not easy to capture the edges using finite element or finite difference method, right? So when you use physics informed neural network, you can get rid of all these problems. Plus, you also don't need to worry about the grid independence of your method, because when you use finite element or finite difference method, you have to show that your problem is grid independence. You have to show that the solution procedure is stable. You can get away with all these problems when you use the physics informed neural network in place of all these numerical methods. So in fact, we are actually going towards the full automation of problems arising in fluid mechanics where neural network is used to solve the problem in the form of partial differential equation and boundary conditions, and these solutions are again fetched to some other neural network to learn about those solutions. So this is kind of full automation of problems arising in fluid dynamics. It is a big change in the field of fluid dynamics. These are the conclusions that I just explained. And it is the development of this first author, Mazaya Raisi et al., which is published in 2019 in Journal of Computational Physics. They are researchers from University of Colorado, and it is a big development. So that is all from my side, given the time frame. And if you have any questions, please ask.
Thank you, sir, for such an amazing and knowledgeable session on AI meets fluid dynamics, a new paradigm shift in fluid dynamics. I believe all of us can learn many things from your valuable session. And thank you, audience, for your attention. If you have any query, please ask to our speaker, Dr. Tripathi.
Hello, sir.
Yes.
Sir,
Just a second. I cannot see the Zoom interface on my screen. Just a minute. Show meeting. Right. Right. Yes.
sir, my question is that regarding stability analysis in fluid dynamics. Sir, here we can apply artificial intelligence, this type of stability analysis to introduce something new.
Yes, definitely we can. You see that the point of stability analysis in fluid mechanics is, you see that when we solve a fluid dynamics problem, the problem always comes in terms of some parameters. As you might have seen in my presentation also, the differential equation that we had,
Yes,
there were
sir.
parameters like Reynolds number or Rayleigh number or those things. Right. So when we use the physics informed neural network, not only we are looking at the changing and adjustment of weights, but we are also, if you can pose it as a problem of determining the values of Rayleigh number or Reynolds numbers for which the solution is stable, then you can use the physics informed neural network to find the stability of the problem also.
Okay, sir. Sir, give me some reference to solve the numerical method for numerical stability analysis.
Numerical methods for stability analysis.
Uh,
Hello.
yes, sir.
Come again. I didn't get you.
Sir, sir, is there any numerical method for solving stability analysis, basically weakly nonlinear stability analysis?
There are not, you can say, numerical methods. There are different methods for finding the stability, different methods for finding the stability analysis. For example, you can go by the method of Lyapunov function to learn about the stability, or you can see, you can actually convert your problem of fluid dynamics by into an stability problem by considering the, let's say, solution about a stationary points, and then you can perturb your solution a little, and then you can find the stability analysis. Like when you have, if you can convert your fluid dynamics problem into an ordinary differential equation problem, then there is this built-in function in MATLAB, BVP4C, which you can use to find the dual solutions, and then you can check the stability analysis, for which the reference I can provide to you.
Okay, okay. Thank you, sir. Thank you.
Any more queries from audience side? Thank you, sir. I, on the behalf of MIT University Madhya Pradesh, would like to thank you for giving your time to share your profound knowledge with us. Thank you so much, sir.
Thank you. And thank you everyone for inviting me and having the patience to listen to me for 1 hour. Thank you.
The session which was postponed yesterday is going to conduct now. So we are fortunate to have with us next speaker, Dr. Pradeep Kumar Sharma. Before his address, it's my pleasure to introduce him. Dr. Pradeep Kumar Sharma is working as a scientist at the University of Southampton, United Kingdom. His primary research area include optimization, mathematical optimization for machine learning. He has worked as a postdoctoral fellow under Dr. D.S. Kothari's fellowship at the Department of Mathematics, University of Delhi, and at the Research Center for Interneural Computing, China Medical University, Taichung, Taiwan. He has delivered many talks at various events in the United Kingdom, Taiwan, and Poland. Dr. Sharma has published over 20 research articles in SCI indexed journals and 2 book chapters of international review. Now, I would like to invite Dr. Pradeep Kumar Sharma to share his insightful knowledge on the topic optimization in the real world applications and innovations. Please, sir.
Thank you, Dr. Ritu, for nice introduction. So, can you hear me?
Yes, yes.
Yeah, okay. Okay, so let me share my slide first, okay? Okay, so can you see my slides?
Yes, it's visible, sir.
Okay. So first of all, I would like to apologize for yesterday. Actually, I have moved to another city for some conference. So I have 2 talks on the same day, and it is the early morning time in the UK right now. So that creates some technical issues for me. And when I joined the talk yesterday, it was too late for me. Okay. So again, apologize for that. So, secondly, I would like to uh, say thank you to the organizers for inviting me to give a talk in this nice workshop. So my talk is based on the optimization in the real world scenario. So I will discuss some kind of applications as well as the latest innovations in the optimization theory in the real world scenario. So my talk is actually threefold. First, I will discuss what is optimization, why we study optimization, and what is the mathematical formulation of optimization. The second uh, goal is to give some real world examples of the optimization problems like in robotics or the some kind of shortest path problems or like some simple real world examples. And the third goal is to the existence of the solution of the optimization problem and the existence of the solution of the optimization problem in the mathematical formulation. Okay, so I will start with the simple question, what is optimization? So actually optimization is derived from the Latin word optimus. That means the best. Okay, so optimization is the act of obtaining best results under certain conditions. Okay, so if you have given uh, some like some finite conditions or some circumstances, then you can find the best output based on that. Okay, so actually when you are optimizing something, this means that you are making it best. Okay, but the best can vary. Okay, it depends on the situation. So suppose that if you are a cricket player and you want to make the most runs or you are scoring most runs, so this means that you want to maximize your runs scored per match. Okay, but at the same times, it is in your mind that your number of matches should be minimum. Okay, so this means that you want to minimize the number of matches. So this example consists both maximization as well as minimization of the runs and matches. Okay, so this is the example of optimization problem where the best can be in different scenarios, like maximizing something or minimizing something. Okay, so in the real life everything can be optimized. Okay, so everything we are doing daily, actually we are optimizing everything. Suppose that we are going to buy food, or we are going to buy something, or we are going to office, then we are trying to minimize the time. Okay, we are taking the shortest route to reach the office. If we are buying food, we are buying the good food at the low cost. So we are trying to minimize everything. So optimization exists in our daily lives. Okay, so now so it is actually the question of knowing what is best and what is the issue and how we can achieve that. Okay, so our goal is to find the best. Now first we need to discover the issue, and then we need to find some method or like the procedure to achieve the best result. Now why we study optimization? Okay, so first, optimization helps us to find the better designs or methods to achieve the best output given under some certain circumstances. Okay, by using optimization techniques, we can design faster evolutions. Like we can design methods which gives the best output under the faster circumstances. We can allocate the resources efficiently, and we can improve the performance of the like some team or some uh, like some machines or anything. Like if some food delivery company is using his manpower to deliver the food efficiently, then he can the optimization can help to uh, uh, optimize the like manpower efficiently, and the uh, uh, and the resources efficiently to provide the food as the with the minimum time and the efficiently. Okay, the other thing, optimization can do the operation efficiency, and we can do the new innovations through the optimization. That is, we can develop new methods, we can develop new technology, we can develop anything new by using the optimization. Okay, so actually optimization works better than the traditional guess and check method. So if you have given some set of choices, and you need to find the best choice in the from that set. Okay, so the one method is to that you will guess that, okay, I will choose this one. So this could not be efficient sometimes, but by using some kind of mathematical formulation or by using some kind of optimization techniques, we can choose the most appropriate or most optimal choice from a set of resources or from the set of choices. Okay, now how optimization problem formulated. Okay, so the first step is we need to describe the problem. Okay, and then we need to gather as much as information to formulate the problem. Okay, the third step is to define the design variables, and by using the design variables we need to define the objective. After defining the objective, the important part is the what are the constraints to find the optimal solution by minimizing this objective. So these are the main steps to formulate the optimization problem. Now, what we need to optimize? So mathematically, we need a objective function which need to be minimized. Okay, so the most important thing is optimization is we need to we want to improve the extreme. Okay, so the sense of extreme could be like maximum or minimum, or maybe it could be different, depend on the way of uh, considering something best. So if, for example, if it is a cost, then we want to minimize, or if it is a profit, then we want to maximize. Or we can consider other example. If we want to go to the office, then we always look for the shortest route. So this is the case of minimization. Okay. Now we call it as objective function, like cost. So cost is the objective function because it must depend on some variable in order to optimization. So the role of decision variables is important because we need to make the decision based on the uh, choices we have. Okay, so these are the variables to which we try to assign suitable values to optimize the objective function. So our optimal decision will be uh, from the set of decision variables. Now the most important part of the optimization problem is the constraints. Okay, so we need to optimize the objective functions within the bounds we have, or within the restrictions we have uh, uh, in our circumstances. Okay, so constants uh, can be functions of the optimization variables. If we are able to formulate the optimization problem mathematically, then we need to find some kind of formula or methods to compute that objective function as well as the constraint sets, and to find the best objective values from the all available values. So this means that we should have either mathematical expressions or numerical methods to compute the values of the objective function and constraints once we know the values of the optimization variables. So now we discuss the mathematical formulation of optimization problem. So mathematically, optimization problem is the mathematical discipline which concerned with the finding the maxima or minima of the function, possibly subject to certain constraints. So optimization problem is to optimize this objective function over a feasible set X. So our goal is to find a optimal choice X such that fx should be minimum over this X. So this optimization problem consists of a objective function which is a real valued function here, but it could be like multi-objective function or set valued function or anything else. And X is the feasible set, that is all the feasible decisions. Okay, so our best choice will be from this feasible set of feasible decisions, and X is the decision variable which will give any one decision variable will give us the best output. So this is an example of the unconstrained optimization problem where we have no constraints of the feasible set, that is feasible set X is the whole uh, real line. So unconstrained optimization problem is little bit easier to consider. So in unconstrained optimization, every point every decision variable is feasible. So actually singular focus is to compute the lower value of f of x if we are considering the minimization problem. If we are considering the maximization problem, then we need to consider the uh, maximum value of the objective function f of x. Now in optimization problem, there could be one variable or there could be many variables. So we can categorize the optimization problem based on the number of decision variables. So the decision variables could be like discrete, that is there are finite number of decision variables, there are infinite number of decision variables, or there are like if the decision variables are infinite, then they are continuous or discrete. Okay, so we can divide the optimization problem based on the decision variables, like they are discrete or the continuous. Now we can impose as many as constraints on the optimization problem. Obviously, when we are we want to achieve our goal, or we want to optimize anything, there are many constraints around that problem. Okay, so the constraint could be unlimited or it could be limited. Okay, so if the constraints are unlimited, then obviously our optimization problem will be very hard, and if the constraints are limited, it would be a little bit easier to solve that optimization problems. So the general formulation of constraint optimization problem is to optimize the objective function f under the certain inequality as well as equality constraints. And these could be like unlimited constraints or the limited constraints. So in constraint optimization, it may be difficult to find the initial feasible point and maintain the feasibility during optimization because of these constraints. So I have already discussed that optimization problem can be classified in two classes. First, based on the problem formulation, and other is the based on the objective and constraint functions and their characteristics. So based on the problem formulation, we can consider like three components. First is the decision variables, objective and constraints. So based on the constraint, we can divide the optimization problem into constraint and unconstrained optimization problem, which I have already discussed the formulation of both kind of optimization problem. And based on the objective function, we can divide the optimization problem into the single objective function, where the objective is mostly the real valued function. Other is the multi-objective optimization. Okay, so we are actually optimizing the conflicting goals in that case. Okay, like we are finding the best output from like some number of vectors. And based on the decision variables, we can categorize the problem into three cases. First is the continuous optimization, or if the variable are the feasible set is continuous. The other is the discrete, or one could be the mixed, which consists both discrete as well as continuous decision variables. Now, based on the objective and constraint functions and their characteristics, the optimization can be classified into different types. The first classification could be made on the based of the objective function, which could be the like a smooth function. If we are considering the smooth objective function, so this could be continuous objective function or discontinuous. Okay, the other could be constant or objective function, could be linear or non-linear objective functions. So the problem can be classified into the linear optimization or non-linear optimization problems. The other classification could be based on the modality, where we can consider the unimodal or multimodal optimization problems. And the most important classification in optimization problem can be made on the convexity. So if the objective function is convex or the constant function are convex, then we can classify the optimization problem as convex optimization problem or non-convex optimization problem. So the convex optimization problem is really important in the real world scenario, because convexity is very important to obtain the optimal solution or optimality of the certain uh, design. Now, the other classification could be made based on the stochastic scenario. So, if there are some certain uncertainty involved in the decisions, then we can classify it as the stochastic optimization problem or the deterministic optimization problem. So my focus is actually more on the problem formulation, not on the classification of the optimization problem, because uh, it is a it is the whole theory. It is not like enough time to discuss all these issues in a short time. So we can find optimization everywhere, maybe in the manufacturing, production, like inventory control, which is very important, like the companies Amazon or the food delivery companies. The role of optimization is very big to control their inventory, or in the transportation, how they can supply their goods efficiently and in a shorter time. Okay. And economics, robotics. So everywhere we use optimization. So now I will consider a very simple example to illustrate that how can we formulate the optimization problem in a mathematical formulation. Okay. So first, my goal is to find the best player from out of these four players based on the most run scored. Okay. So I am considering four players. So this will be our feasible set. This means that these players are our decision variables. Now I need to find a rule which gives the number of runs of each player. Okay, so I call that rule as the function f. So now, since we need to find the best player which has scored more runs, so this means that we need to we need to find the maximum value, or we need to maximize our objective based on these decision variables. So this problem can be cast as a maximization problem. So we need to find this X player from this set of players such that number of runs are most for this player. So we can see that Sachin has scored the most number of most runs. So this means that the best output or best feasible, best optimal point will be the Sachin, and best optimal value will be this. Okay, so this is the simple example which illustrates the mathematical formulation of an optimization problem. Now there is other very famous problem of the optimization formulation, which is known as the Fermat-Weber problem. Okay, so suppose that you have a list of your loved one who live in a given location in India, and you want to decide live near among them. Okay, so you want to stay close to them, like at some places your mom and dad is living, at some places your sister lives, and your relative lives at different positions, and you are here. Then you try to minimize your distance to each one. Okay, so this means that the goal is to minimize the sum of distances to each person. So this means that how can we formulate this problem as an optimization problem? So this is a very famous problem around 1870 or 1890. So here location of the person I can be represented as the xi. So, and our location is this, we denote it as the y. So we need to take decision based on our location. Okay, so now we can cast it as a minimization problem. So we need to minimize over the over my location or our location such that we can minimize the sum of distances between with each person. Okay, now there could be some constraint. Okay, so suppose that your mom is saying that you care more uh, about her than his sister. Okay, so she is saying that you should care about me more than your sister. So this means that we are we are imposing some restriction. Okay, so this means that we are imposing some weight vector, okay, or some weights to that optimization problem. So this means that we can rewrite this optimization problem by using some additional constraints over this optimization problem. So this is very interesting example of the optimization problem uh, to find the minimum distance with your neighbors or with your relatives in your locality. Now we can consider another simple example. Suppose that a dog is sitting next to a swimming pool and his owner threw a rubber duck into the pool. The dog can run on the pool tiles as twice as fast as he can swim in the water. Okay, so there could be some possible routes he can reach to this duck. Okay, so the question is that what path should the dog take to touch the duck in the shortest time? So actually shortest path will be the straight line between the duck and the dog. Okay, but this is not the solution uh, for the dog to reach the duck. Okay, because the dog can run fast at the tiles, but he will take more times in the water. So actually we are not only interested in the shortest path, we are actually interested in the shortest time path. Okay, so both the path as well as time should be the shortest. So what are the variables here? So the variables are these continuous paths, which could be as many as we want. Okay, so uh, most probably the dog will take this path to reach the duck, and this problem can be cast as a calculus of variation problem uh, in the form of a optimization problem. So the goal is to find the optimal path to reach the dog to the duck. Now there is another very interesting example of optimization problem, which is the traveling salesman problem. Okay, and this problem is the NP hard problem. So the actual goal is to uh, find the shortest possible route that visit each city and returns to the origin city. Okay, so suppose we start from here. So our goal is to find the shortest distance so that we can reach we can cover each city, and again by using the shortest path we can return to the original city. Okay, so the problem is that how to find the shortest path through a series of points. So it is not as simple as it seems. Okay, it is NP hard problem. So the approach is first calculate the distance between all the combination of the points. Okay, so first task is to calculate the distance between all available points. Okay, now solve this as an optimization problem where variable corresponding to the trips between 2 points. Okay, so now we need to solve this as an optimization problems where variables are the trips between this point or this point. Okay, and we will give the route as 1 or 0. Either we are going through that route or we are skipping that route. So now if we are formulating the traveling salesman's problem as an optimization problem, then decision variables are the binary vectors based whether the trip exists or not. So decision variables are the binary variables where we are considering that does the trip happen or it doesn't happen. Now, what are the objective? So the objective is to minimize the distance traveled between 2 points, okay, or between the initial point to the final point. But the constant is that each stop only 2 trips. Okay, we need to try to minimize the route. Like if we have crossed one route, then we will try not to return that route, and then we can solve this optimization problem by using the integer linear programming algorithm. That is, this problem can be cast as an integer optimization problem. Now the latest advances in the optimization theory is the multi-robot task allocation problem. Okay, so it is quite new research area in the from a optimization theory perspective. So actually the goal is concerned with the situation when a set of given tasks must be performed by a team of mobile robots. Okay, so our intention could be optimizing an objective function. Okay, so it could be the optimizing the mission time, it could be rescue someone from the mountains or from the sea or from from anywhere, like some disaster occurs, like uh, some disasters occur and we want to rescue someone from there, then we can take help of the mobile robots to rescue someone. Okay, so mobile robots are actually of 3 types. First are the unmanned ground vehicles. Okay, so it could be like some land-based robots that could be like wheeled, tracked, or legged. Okay, so these kind of vehicles will work without manpower, and these are totally land-based. Other are the unmanned aerial vehicles, okay, like drones or planes. Okay, but we don't in drones we don't need men to operate. We can operate drones from anywhere. Okay, so this is also the important mobile robots which is known as unmanned aerial vehicle. And the third are the autonomous underwater vehicles, which mainly are water-based robots that operates on the surface of the water or inside the water, like in the sea. If we want to rescue or search something in the sea, then we can use underwater vehicles. If we don't have the ground connectivity, then we can use the unmanned aerial vehicles, and if we have the ground connectivity, then we can use the unmanned ground vehicles. For example, suppose that if fire hazard occurs in a forest and we don't have the road connectivity to stop the fire, then we can use unmanned aerial vehicles to drop the water capsule in that area or to search or rescue someone from that area. So the problem of deciding which robot should execute a given task is called a multi-robot task allocation. So actually we have number of robots and we have number of tasks. Then we will allocate each robot each one task, or we can allocate multiple tasks. Okay, so this problem aims to coordinate a large number of robots in order to compute a set of tasks with certain constraints. Okay, so in this problem we assign tasks to robots in order to maximize or minimize a given objective function, and the objective function could be like mission time, or to search someone or to rescue someone from somewhere. Okay, so the advantage of this using the unmanned vehicles for the task allocation is that they can like work in the high level of difficulty, or other in the unexpected events, like if weather is not working as good or wind direction is very high, then these kind of unmanned vehicles can work in these kind of unknown environment, even though there are chances of failures of these unmanned vehicles in uncertain environments. So we have certain set of unmanned vehicles, and we have to allocate to some number of tasks to each unmanned vehicles, or we can call robots. So the interesting part is that this problem can be cast as an optimization problem. So suppose that we have a set of n tasks and we have set of n robots, and we need to assign one task to each robot. Okay, and Cij denotes the matrix that define uh, the cost of each robot task. Now the variables of the decision is considered as 1 if robot I is assigned to accomplish the task J. Otherwise, we will consider that no task is assigned to the robot. So the goal is to assign suitable robots to the task in a way that minimize the total cost of mission under the constraints. Okay, so we want to minimize the total cost of the mission here by using the cost matrix and the uh, number of tasks as well as number of available resources under certain restrictions. Okay, so in this problem we are considering that each robot is assigned one task only, and this can be cast as an integer linear programming problem. So this area of research is very new, and the work is in initial stages. So we can not only formulate this problem as an integer linear programming, we can also formulate it as a non-linear program, we can formulate it as a general optimization problem, or we can formulate it as like bi-level optimization problem, or any continuous optimization problem, or any other optimization problem, and accordingly we can use the technique to solve this kind of optimization problem. Now I will uh, try to illustrate the importance of the optimization problem into machine learning. How can machine learning problem be formulated as a optimization problem? So the first question is that why we need to study machine learning. Okay, so machine learning is used to model data, make predictions, and we can build many intelligent applications from the machine learning. So all these applications uh, are the result of the machine learning or artificial intelligence techniques. Like for example, the simplest example is the WhatsApp. Okay, if you are typing a message to someone using your keypad, then you can observe that when you are typing a word, you can see that uh, on the title bar you can find the next word. Okay, so it is actually predicting the next word of the sentence. Okay, so this is the artificial or machine learning techniques which is already predicting the next word based on the experiences which you always use to send messages to someone. Okay, so this is the simplest example of machine learning in the current scenario. Now, how machine learning works? So we have a some kind of raw data, and we identify the features of that raw data. We identify certain features, and then we process the model, and then it will make the predictions based on the uh, based on these features. So both machine learning technique or artificial intelligence techniques work on the same process, and both are the decision making problems. So for example, suppose that we have a raw text, that is, it is a puppy and it is extremely cute. So we have some kind of phrase, and we want to classify that, or we want to make prediction that it is puppy or not. Okay, so we will give some features like some numeric inputs like 1 or 2 or 0. If it is not puppy, then we will give it 0 value, or if it is certain word, then we will represent it as a alphanumeric uh, features. So after processing, it will classify that either it is puppy or not by based on the learning experience. Now, almost all machine learning problems can be expressed as a optimization problems. Okay, so suppose that we have a input xi and we have a desired output yi, and we have a certain hypothesis function which will process our input to the output defined on the parameter theta. So we want to optimize this loss function, which is the value of the difference between the actual value and the predicted value. Okay, so machine learning algorithm are the optimization problem to minimize this loss function over certain parameter theta, and this loss function is the value between the prediction as well as the actual value, and we want to minimize that uh, difference between the actual and the prediction uh, prediction value. So since every machine learning problem can be cast as an optimization problem, so this is the important research area in the current scenario. Now I will talk about from the mathematical perspective, how can we find the solution of an optimization problem. So first I will define the local minimum of a optimization problem. So any point x bar in a feasible set x is a local optimum if f of x bar is less than equals to f of x, within some neighborhood of the x bar. Okay, so in this figure we can see that these values are all at the all of their lowest. Okay, but we cannot observe that which is the actually minima. So these points are minimum locally. Okay, so these are all the local minima uh, in this picture. Now similarly we can define the strict local minimum if f of x bar is strictly less than fx in the neighborhood of x bar. So in this figure we can see that this is actually the strict, you can say that local minimizer, but here we are also getting the strict global minimizer because there is no other local minimizer here. So this is the strict local minimizer or the strict global minimizer, but it has many local minimizers. Like in the surface we can see that this could be the local minimizer, this point could be the local minimizer, this could be the local minimizer, and many modes. Now in optimization, the global optimum is the important. Okay, so any feasible solution or feasible variable is a global minimum if f of x bar is less than equals to f of x. That is, this value is minimum from the all feasible values over this objective function. Okay, so in general, finding local minimum is less ambitious goal than finding the global minimum. But in practice, most of the optimization problems are high dimensional and non-convex. So we need to find the local minimum to find the best, to achieve the best output. So in this picture, we can see that there is no lowest point than this. So this is the global minimum. Okay, this is also minimum, but this is the local minimum because we can find this point uh, uh, more lower than this point. Okay, so we can observe that this point is the local minimum and this point is the global minimum, and every global minimum is also a local minimum. Now the question is that is the optimization problem always guaranteed to have an optimal solution? So the answer is no. Okay, so mathematically if we consider the feasible set as this and we define the objective function as a linear function, then we can observe that this optimization problem has no optimal solution. So it is not necessary that an optimization problem need to have an optimal solution. Okay, now what are the sufficient conditions for an optimization problem to have an optimal solution? So the first mathematical result is the very well-known Weierstrass theorem, which says that a continuous function over a non-empty and compact set always achieves an extremum, that is minimum and maximum. So this is the well-known existence result for the optimization problem. Now the question is that can we weaken this compactness assumption in order to get the optimal solution? So the answer is that yes, we can weaken this compact assumption, but we need to use some kind of coercivity assumption in order to get the optimal solution. So the other condition is that every continuous function over a non-empty and closed set, and if this continuous function satisfies certain coercivity condition, then we can find the optima of this optima of the optimization problem defined by using this objective function. Okay, now the other condition is that can we remove both closedness and boundedness from the constant set? So the answer is yes. We need to consider the sublevel set, and if we are considering that this sublevel set is non-empty and compact, and f is continuous function, then in that case we will also get the optimal solution of the optimization problem defined by using this objective function. So the conclusion is that if f is a continuous function and any one of these conditions is satisfied, then we will get the optimal solution of the optimization problems defined by using this objective function. Okay, so in all of these conditions we have looked that we can weaken the compactness assumption, or we can remove the compactness assumptions. So now the question is that can we weaken the continuous assumption? That is, can we weaken that f should not be continuous? So the answer is yes. Okay, if the feasible set is non-empty and compact, and we can consider f as a lower semi-continuous on x, then even in this case we can get the optimal solution of that optimization problem. So in general optimization problem, we consider this assumption, that is lower semi-continuous function on a non-empty and compact set achieves minima. Okay, so these theorems gives the existence of optimal solution of an optimization problem. Now we can find several examples in which we can see that if we can not exclude any assumptions from these results. So suppose that we defined a real value function like this, then we can see that there is no minima because f is continuous but domain is not compact because domain is not bounded. So we cannot drop the boundedness assumption in order to get the optima. Also, we cannot drop the closeness in order to get the optima. If we define the function like this, then we can see that this domain is not closed here. Even though f is continuous and this domain is bounded, we are not achieving any optimum here. The other example could be like we cannot drop the continuity assumptions from that results. Like if f is the function defined on a closed interval 0, 1 in such a way that it achieves the value x whenever x is not equals to 1, and it achieves the value 0 when x is 1. So we can see that there is no maximum because domain is compact but f is not continuous function at 0. So this means that Weierstrass theorem gives the sufficient condition for the existence of optimal solution, but it is not necessary in order to get the existence of the optima. So we can consider this nice example. So our feasible set is this, and we have defined the objective function in such a way that, so we can see that f is discontinuous function and constant sets is neither closed nor bounded, even though we achieves the optimal solution at x equals to 0. Okay, so x equals to 0 is the optimal solution for the optimization problem formulated by using this objective function. Now the question is that can we achieve the infimum of this optimization problem when x is not compact? So the answer is yes. I have already told that we need to impose some kind of coercivity assumption in order to weaken the compactness of the feasible set, or as well as some kind of convexity structure on this feasible set. Okay. Now what if we don't have any coercivity or convexity assumption on this feasible set? Okay. So in that case, we cannot get the exact solution of the optimization problem, we can consider the approximate solution of that optimization problem. Since the optimization problem are high dimensional and non-convex, in practice, it is very difficult to find the uh, exact solution. Like in machine learning problems or the task allocation problems by robot, it is very hard to find the exact solution. So most of the time we consider some kind of approximate solution. So we can define an approximate solution if a point that satisfies this assumption or condition is known as the approximate solution. So how can we give the existence of this approximate solution? So the well-known equivalent variation principle guarantees the existence of this kind of approximate solution where neither we need any kind of compactness or convexity assumption on this feasible set. So equivalent variation principle obtain the approximate solution on a semi-continuous bounded value functions over a complete metric space. Okay, so we can observe that if our acting space is a complete metric space and our objective function is proper bounded below and lower semi-continuous. Okay, so we are not using any closed or boundedness condition, we are using bounded below condition only, and we are using lower semi-continuity. Then under we can find an approximate solution x bar which satisfies these conditions. Okay, so the well-known equivalent variation principle gives the existence of the approximate minima for a certain optimization problem. So this is all about my talk. It is actually based on some very obvious concepts, examples in the optimization problem. It is actually not based on my research work. Okay, even though if someone is interested in my research work, like in machine learning or in set optimization or in vector optimization or multi-objective optimization or in robotics, then he can uh, he can look at my Google Scholar profile or on my profile to, and if he is interested, then he can contact me by using my email. Okay, so this is all about my talks. Thank you for your kind attention.
Thank you so much, sir, for sharing your knowledge with us. Your valuable insights and perspectives have been beneficial for us. The session is open for question and answer now. So if you have any queries, so you can ask to our speaker, Dr. Pratikema Sharma. Thank you so much, sir. I, on the behalf of MIT University Madhya Pradesh, would like to thank you for giving your precious time. The next session will start at 2 p.m. and kindly join with the same link. Thank you once again, all of you, for joining the session. Thank you, everyone.
Okay, thank you for inviting me for a talk. Okay.
Hello. Am I audible?
Yes, sir. Can I start, sir?
Yeah, am I audible?
Yes, yes, sir.
Okay, that's great. So you may start now. Yeah.
Okay, ma'am. Please, ma'am, start.
Yeah.
Good afternoon and welcome all to the afternoon session of International Workshop on Recent Trend in Applied Mathematics for Engineering and Technology. We are fortunate to have with us next speaker, Dr. Balendu Bhushan Upadhyay, sir. Before his talk, it's my pleasure to introduce him. Dr. Balendu Bhushan Upadhyay is working as Associate Professor in the Department of Mathematics at IIT Patna. His research interests include nonlinear optimization and multi-objective optimization. He has authored or co-authored in many SCI indexed research publications. Many PhD, MSc, MTech students are doing research under his guidance. He has 4 projects like DST and TechCube in his credit. He has served as a technical program committee member, a reviewer, and a committee member in several reputed national and international journals. He has published more than 50 research articles. He delivered several talks in USA, UK, IIT Indore, and IIT Patna. Now I request Dr. Upadhyay sir to deliver his talk on the topic unconstrained optimization and step descent method. Please, sir.
Yeah, so thank you very much, madam, and I will also like to thank the organizer for and also Dr. Ram Kumar for providing me this opportunity to talk in that seminar. And I'm so happy that such a program is going to be organized, and it is happening successfully in IT in this MIT University. So thank you very much again, and so I will start. So topic of today's talk is unconstant optimization and steeper descent method. So first I will talk what is this unconstant optimization, then I will go in more detail about the steeper descent method. So this is outline of this talk that I will discuss what is unconstant optimization, then I will talk about line search and descent direction, and then I will discuss about the steeper descent algorithm in different situations when we have constant step length and we have variable step length, and then I will do the convergence analysis. So we all are aware about optimization problem, and we know that it happens everywhere. Wherever we go, whatever we want to do in real life, always we do optimization, right? So optimization problem are just identified by an objective function which we have to minimize or maximize subject to certain constants. So those constants would be like some subset of Rn, or sometimes they are written explicitly as functional constant, right? So there are two types of optimization problem. When this set omega, which is subset of Rn, it depends if it is equal to Rn, then this problem is called unconstant optimization. And when this is subset of Rn, then this is called constant optimization. So in today's talk, I will be focusing on unconstant optimization, where omega is subset of Rn. So just let us just recall the notion of local minima and global minima. So if f from Rn to R be a real valued function and defined on some subset omega of Rn, then a point x star is a local minimizer of f over omega if there exists epsilon greater than 0, such that we are getting a ball centered at x star with radius epsilon, such that for every point in this ball, we have that condition that fx would be greater than or equal to fx star. Means the value of the function at this point x star should be less than or equal to every value in some neighborhood of the point x star. So if that property is satisfied, then we say that the point is a local minimizer. And if the value of f at x star is less than or equal to every value in the domain omega, then the point x star is called a global minimizer. Okay. So we can just see from this picture here that x1, x2, x3, they all are local minimizers, right? But when we just use the definition of global minimizer, we see that the point x1 is a global minimizer, right? Why? Because the value at the point x1 is less than or equal to every value in the domain of this function. So we see that x1, x2, x3 all are local minimizer, but x1 is the global minimizer. So when we deal with a function of n variables or multivariable function, then we require the notion of derivative and notion of Hessian. So this because you know that if function depends on n independent variable, then accordingly we have n partial derivative. And if you write n partial derivative as a vector, we get our derivative matrix. And if you take the transpose of derivative matrix, we get the gradient of the function. And again, we can talk about the second order derivative as well. And second order derivative will be the derivative of the derivative. And you can see that this is the n by n matrix consisting of n square partial second order partial derivative. So this is called Hessian of the function f. And if just we differentiate, suppose we have function y transpose ax, right? And if you have to get the derivative of that function with respect to x, then its derivative will come out to be y transpose a. And if we have a quadratic function x transpose ax, its derivative will be x transpose a plus a transpose, right? And if A is a symmetric matrix, then derivative of x transpose qx will be 2x transpose q, because A is equal to A transpose. And if we have to get the derivative of x transpose x, this will be simply 2x transpose. All these things will be required in our subsequent discussion. That's why I'm giving you insight about that one. So, and then let us see that what is the descent direction, right? So when we just do the optimization of this function f from R into R, right? So because we want to minimize this function, right? So what we do, because if you don't know the exact value where we get the minima, then what we do, we just proceed in a line search. We proceed in a line. We start with the point xk and then proceed to the next iteration by using the formula xk plus equal to xk plus alpha dk, right? So basically we are interested in a direction d where we get some decrease in the value of the function, right? So if we are at the point x, then at the point x, direction d is called a descent direction. If we are able to get some alpha bar greater than 0 such that f of x plus alpha d is less than fx. So if this property is satisfied at the point x plus alpha d, right, then the direction d is called a descent direction, right? So there are several descent directions because and one of the most prominent is the negative of the gradient of the function, right? Later I will show that why this is the like steeper descent direction, but just for the timing, let us assume this is a descent direction, and I will prove that why this is descent and why this direction is steeper descent. And depending on this line search, right, there are other directions as well where we get decrease in the function, and one is given by Newton's descent direction, and this is given by minus hfxk inverse minus gradient of xk, right? So where hfk is the Hessian of the function f at xk. So this is basically inverse of the Hessian at the point xk multiplied with the gradient of xk. So if you proceed in this direction, we'll also get the descent. We also get the decrease in the value of the function. Similarly, if you just approximate, because most of the time we are not having, quadratic function. So if you have any general function, we need to just approximate the Hessian matrix, because computing the Hessian is going to be very computationally expensive. So what we do, we just use approximation of the Hessian. And when you do that one by this formula, right? So this is known as a quasi-Newton method, and there your direction is given by minus bk inverse gradient of xk, where bk is updated by this update formula, right? So if that direction is used, also this provides such the descent, and this is one of the descent direction. So now I will just discuss why we are interested in the steeper descent direction when we are doing line search, right? So suppose we are at the point xk and we have to move in the direction dk. So we see that we have many directions available, like steeper descent direction, like Newton direction, like quasi-Newton direction. There are many directions available with us where we can get a decrease in the function, right? So if we are moving in a, like a small step length alpha k, right? So then we reach to the next iteration, that is called xk plus 1. So xk plus 1 can be given by xk plus alpha k is the step length and dk is the direction. If you are following this one, this is called line search, right? So you see that here we have two important things. One is the step length alpha k, another is the direction dk. So dk is most of the time we take the descent direction, and alpha k is the step length, right? So there are many methods to determine the step length alpha k, because we know that if alpha k is like bigger one, if you take very big alpha k, number of iterations will reduce. But there could be a problem that with big alpha k, right, we are having a zigzag motion, right? And if we take very small alpha k, right, then number of iterations will increase. So that's why we want the optimal alpha k, right? So we will discuss that one. So for further discussion, we require to understand what is the symbol O, little o of little o symbol. So to define this one, let f be a function from omega to Rn. This is vector valued function, and this is defined in domain omega subset of Rn, and that domain includes 0, right? And let G be a real valued function. This is defined in the neighborhood of 0, and G is not 0 when x is not 0. So we say that fx is little o of gx, if limit x tending to 0 and x belonging to omega, norm of fx by mod of gx is 0, right? So this symbol is used to replace different type of error function that we know and we use in Taylor's expansion, right? So you know that in Taylor's expansion, you see that you have different types of error terms like Lagrange term, Cauchy term, right? So to just unify that idea, the notion of Little have been given, right? So this will provide you the idea that how we are making a change in the h. So if we say that fx is equal to little o of gx, then using that definition, we can just show that x square can be written as little o of x, because we can check that mod of x square upon mod of x is 1, right? And that is x, and when x tends to 0, this will be 0. Similarly, we can show that this vector x cube and 2x square plus 3x to the power 4, this can be written as little o of x, because if we take the norm of this vector and divide it by norm of x, we will get 0. Similarly, we can write the x cube equal to norm of x square and x equal to norm of 1. So that symbol will be used, and we have this Taylor's theorem. So assume that f is a function from Rn to R. Suppose f is a C2 function. C2 means function is twice differentiable and second order derivative is continuous. Then Taylor's expansion in terms of little o can be written like this. So fx equal to fx naught plus gradient of fx naught into x minus x naught plus x minus x naught transpose Hessian of f at x naught into x minus x naught plus little o of norm of x minus x naught square, where little o of x minus x naught square tends to 0 as x tends to x naught. So this is Taylor's expansion of second order, and we will be using that in our further analysis. So let us talk about the steeper descent algorithm. So that algorithm was proposed by Cauchy, right, where he proposed the use of the gradient as a way of solving a nonlinear equation. So we'll see that because you see that this direction of gradient, because that depends on the function, on the variable x. So we see that if we are at the different point, right, your derivative will be different. So derivative is a local property, right? So we can just see here that if we have a label curve of a function, right, different label curves of a function, and suppose we are starting from this. So if you move at, suppose we are starting with the point x naught and we are moving there in the direction of gradient. So we will move to the next point x2, and then you see that direction of the gradient at the point x2 is different. And again at the point 3, it is different. So we see that this is always varying. This is not something fixed. So that's why this direction that we are getting, this is like a local behavior of the function, because that is in terms of the gradient of the function. So now we'll prove that the gradient vector is in the direction of steepest ascent, right? So it means what? It means that if you move in the direction of the gradient of the function, we will get, this is the direction where we have, fastest rate of increase of function, right? And then we will prove that if you move in the direction of negative of the gradient, then this direction will be the direction of steepest descent. So let's just consider that suppose we are in Rn, we have some point x there, and let f denote the value of the function at the point x. And now consider a neighborhood point of x, that is x plus dx, where dx is a small change in all component of x, that is x1, dx1, dx2, dxn. So if you make a small change in x, that is x plus dx, there will be corresponding change in f. So suppose that change in df. So change in x, so that is dx. So if you get the norm of dx, that is dx transpose dx. So this will be equal to length of the vector. This is ds square, and this will be equal to I from 1 to n dxi square, right? So this is the magnitude of the vector dx. And because we are make a change in x to x plus dx, so there will be change in f. Suppose that change in f plus df, right? So if x move from x plus dx, f value changes from f to f plus df, and df can be given in terms of that expression. So df can be written as sigma I from 1 to n del f by del xi into dxi, and that will be equal to inner product of gradient of f into dx, right? So you know that length of dx is ds. So if u is a unit vector along the direction dx and ds is the length of dx, then this is the relationship between dx and ds. Dx is equal to u ds, right? So if you use this one, so you can just write df by ds can be written as df by dx into dx by ds, right? And df by dx is nothing but gradient of f multiplied with dx by ds. And you can see from equation 4 that dx by ds is equal to u. So what we get the df by ds equal to gradient of f into u. It means that rate of change of function with change in s is equal to the inner product of gradient with the unit directional vector in the direction of change. So if you just just take the norm of both sides, so we get that df by ds is equal to gradient of f into norm of u into cos theta. So where theta is the angle between gradient of f and u, right? So this will provide the rate of change of f with respect to s, right? So if there is a change in the length of x, the corresponding change in df will be given by this relationship, right? So that will provide you the rate of change of f with respect to s. So what we see? We see that rate of change of f with respect to x is equal to gradient of f into norm of gradient of f into norm of u into cos theta. So you see that norm of u is 1 because u is the unit directional vector. So everything you see that depends on the angle between gradient of f and u. And we know that cos theta is minimum when theta is 180 degree, and this is maximum when theta is 0. So we see that there will be maximum change when you have the same direction as the direction of gradient, and this will be minimum when they are in the opposite direction, right? So from here what you get? We get that if you move in the direction of gradient, then we will get the maximum change in the function, because this is the direction of maximum change in the function, maximum increase in the function basically. And if you move in the opposite direction of gradient, that is minus gradient of f, we will get the maximum decrease in the function, right? So that's why the direction of negative of the gradient is called the direction of steepest descent, and the direction of gradient is called the direction of steepest ascent. And we can see it here from that picture. We see that this black direction is the direction of gradient. So we can see that here the function increasing. But if you move in the opposite direction, negative direction, we see that we have descent there. And direction of minus gradient will be the direction where we have maximum rate of decrease of function, right? So that's why negative of the gradient is known as the direction of steepest descent. And we can just check it using the Taylor's expansion. We can check that if you move in the direction of negative of gradient, we will get a descent in the function. Because if you apply this Taylor's theorem, we see that f x naught minus alpha into gradient of x naught, that can be written as f of x naught minus alpha into gradient of x naught into gradient of x naught for little o of alpha. And because if gradient is not 0, means we have not reached to the optimizer, then for sufficiently small alpha, we can check that f of x naught minus alpha, gradient of x naught is less than fx naught. It means what? It means that if from the base point x naught, if we move at a small distance in the direction of negative of gradient, we will get a descent in the function. We will get a a decrease in the function. So what we get from here, we get that the direction of negative of the gradient is a descent direction. And from previous decision, we know that this is the direction of steepest descent, right? So now if you just modify our line search method, where our direction dk is replaced by minus gradient of fxk, then this is called a gradient method. This is called a gradient method. And along with that, if we just choose alpha k as optimal step length, so this is called steepest descent method, right? This is called steepest descent method. So if we are not choosing alpha k as a optimal step length at the point xk, then this is called gradient descent method. This is called gradient descent method because we are moving in the direction negative of the gradient. But if we just also optimize alpha k, then this is called the steepest descent method, right? So our algorithm can be written like this. Let x naught be then arbitrary point and set k equal to 0 here, and then find the search direction dk, and dk is negative of the gradient at the point xk, and then we just determine the optimal step length alpha k. Optimal step length alpha k will be determined by this formula. Alpha k is equal to arg minimum of f of xk plus t dk for every t positive, right? So this for all non-negative values of t, that very value which give you the minimum value for this function f of xk plus t dk, that is called the optimal step length, right? So if we have the optimal step length and we have this direction negative of the gradient, then this method that is based on these two things, that is xk plus 1 equal to xk plus alpha k dk, and that is is xk equal to xk minus gradient of xk. This is called steeper descent method. We can just see, we can check a very simple example. Just consider this function x1 minus x2 plus 2x1 square by 2x1 x2 plus x2 square, and suppose this is start from the point 0 0, right? So we have to apply the steeper descent method. So first of all, we have to find the gradient of the function. So as we know that this is function of two variables, there will be two components in the gradient. So that is del f by del x1 and del f by del x2, and this will be come out to be just 1 plus 4x1 plus 2x2 minus 1 plus 2x1 plus 2x2. And because we have to find the direction at this point 0 0, so gradient at this point come out to be 1 minus 1, and d naught is minus gradient of this point. So this is the direction where we have to move. Now we have to determine the step length, and since we are applying steeper descent, so we will just find the optimal value of the step, right? So we have to determine this lambda, arg minimum of lambda non-negative for f of x naught plus lambda d naught. So x naught is given. Now we have d naught. So f now becomes a function of lambda only. F x naught plus lambda d naught will be equal to f of minus lambda and lambda, and this will be equal to lambda square minus 2 lambda. And to find the optimal value of lambda, just differentiate this function, and df by d lambda equal to 0. So we get lambda equal to 1, right? So now we have the step length lambda and we have the direction. So we can get the next iterate, and that will be given by x1 equal to x naught plus alpha naught d naught. So this will be equal to 0 0 plus 1 into minus 1 1, and this will be minus 1 1. And we see that because gradient at this point is not 0, so this is not optimum. It means that we have to continue the process, right? So now again we have to find the direction and the step length, because I have told you that derivative, because this is a local property, at every point we have to determine the direction. So now we have to just find the direction at the point d1. So by that method, this will be given by minus gradient of fx1, and this will be 1 and 1. And again, we have to determine the step length. So we have to consider this function f of x1 plus lambda 1 d1. So we have x1, we have d1. So now f becomes function of lambda, and so basically f is function of minus 1 plus lambda and 1 plus lambda. And just putting all this value in the expression for f, we get that 5 lambda square minus 2 lambda minus 1. To get the optimal step length at this point, differentiate f with respect to lambda equate to the 0. We get lambda equal to 1 by 5. So step length at this point is 1 by 5. Now we get the next iterate, that is x2 equal to x1 plus alpha 1 d1. And this will be equal to minus 1 1 plus 1 by 5 into 1 1. And this is minus 0.8 and 1.2. Right? So, and again, if you check the derivative at the point x2, we see that this is 0.2 and minus 0.2. This is again not 0, means we have to continue the process, right? And we have to continue until we get the optimum, that is minus 1.0 and 1.5. Right? So there are certain properties that steeper descent method have. And first one is that if you move from x1 to x2, so we see that direction is orthogonal to the direction when we move from x0 to x1, right? It means that let xk be a sequence that we get out of steeper descent algorithm, and for the function f from r into r, then for each k, the vector xk plus 1 minus xk is orthogonal to the vector xk plus 1 minus xk plus 1, xk plus 2 minus xk plus 1, right? So we can see here that xk plus 2 minus xk plus 1 direction is orthogonal to xk plus 1 minus xk. This is one of the prominent property of steeper descent. So we can prove it. So if xk is a steeper descent sequence for f from r into r, and if we have not reached to the optimum, gradient is not 0, then also we can prove that f of xk plus 1 is less than f of xk, right? It means that the direction of, through steeper descent method, we are always moving in the direction of descent, right? So each iterate will provide you a value of the function which is still less than the value at the earlier iterate. Now just we have to just do some further analysis about how the convergence of stable diffusion method will work. So let us consider a quadratic function, right? So, and we will just do the analysis for the quadratic function, and then we will do the analysis for a general function, right? So let us consider a quadratic function of this type, fx equal to 1 by 2 x transpose qx minus b transpose x, right? So here q is a symmetric positive definite matrix, and b belongs to Rn and x belongs to Rn. So gradient of f will be equal to qx minus b because q is symmetric positive definite. And now we use the symbol gk to denote the gradient of fxk. So gradient of f at xk will be qxk minus b. So gk is nothing but qxk minus b. Using all those symbols, we will do some further discussion on this one. So we see here that if you are so here our stable diffusion method now will be like this: xk plus 1 equal to xk minus alpha k gk, right? Because gradient of that function is qx minus b, and that is denoted by gk. So our method for quadratic function can be written as xk plus 1 equal to xk minus alpha k gk, where alpha k is the arg minimum of f of xk minus alpha k gk, where alpha is non-negative, right? So in the quadratic case, we can find an explicit formula for alpha k. And if we assume that if gk is not 0, or if gk is 0, then xk is x star and the algorithm stops. And because alpha k is non-negative, is a minimizer of this function, we apply the first order necessary condition. So phi k prime alpha must be equal to 0, and phi k prime alpha for this function will be xk minus alpha gk transpose q minus gk minus b transpose minus gk. So what we get? We get that if you equate phi k prime alpha equal to 0, applying first order necessary condition, so alpha gk transpose q gk will be equal to xk transpose q minus b transpose gk, right? So value of alpha we can get here, and this will be like alpha k is equal to gk transpose gk upon gk transpose q gk. So in case of quadratic function, in other than in a general function, we have a explicit formula for the step length alpha k if you are applying steeper descent method, and that will be given by gk transpose gk upon gk transpose q gk, right? And we will see here that if we define another function vx, where we are adding some constant term, because suppose we are minimizing the quadratic function x transpose qx minus b transpose x, and suppose x star is the minimizer, x star is the minimizer of the function. So if x star is the minimizer, then gradient is 0, and if gradient is 0, then qx star must be equal to b, right? It means that solution of our uh, minimizer of this quadratic function will be given by x star equal to q inverse b, right? So now just consider another function vx, which is fx plus some constant, because x star is fixed, q is positive definite, so x star transpose qx star will be a real number, positive real number, right? So vx is nothing but fx plus some constant c, and using this one, vx can be written as 1 by 2 into x minus x naught transpose x star transpose q into x minus x star. So this is your vx, right? So now we just see that v differs from m only by this constant 1 by 2 x star transpose q x star, right? So if you are applying this steeper descent method for quadratic function, then xk plus 1 will be equal to xk minus alpha k gk, where gk is qxk minus b, and we will see that this relationship that vxk plus 1 is equal to 1 minus gamma k into bxk will be satisfied. This relationship will be satisfied, right, by the function v, where gamma is a constant, gamma k is a number, and this will be given by alpha k gk transpose q gk upon gk transpose q inverse gk into 2 gk transpose gk upon gk transpose q gk minus alpha k. And we can see that if gk is 0, then gamma k is 1, and if gk is not 0, then gamma k have that expression, right? So if you use this value of gamma k, vxk plus 1 and bxk can be written by this highlighted equation. And using this, you can just see that because gamma k will be become like 1 minus gamma k will be vxk plus 1 upon vxk. So gamma k will be equal to 1 minus vxk plus 1 upon vxk. And because vxk is positive, so what we see that gamma k is always less than equal to 1, right? Because gamma k is 1 minus vxk plus 1 upon vxk, right? And because q is positive definite matrix, so x transpose qx and all this thing going to be positive. and because this is going to be gamma k is 1 minus vsk plus 1 on vxk, gamma k will be always less than equal to 1 for every k. And if gamma k is 1 for some k, then we can see that then vxk plus 1 is 0, which is equivalent to that xk plus 1 equal to x star, means you reach to the optimum value. And we can just also check that for every I bigger than or equal to k plus 1, xi equal to x star and gamma k is 1. And the other relationship that the gamma k is 1 if and only if either gk is 0 or gk is an eigenvector of q, right? So we see that our whole analysis is going to dependent on the behavior of this sequence gamma k and the series which is made of gamma k. So gamma k have certain property. We know that gamma k will be less than equal to 1 for each k, and gamma k is 1 if and only if gk is 0 or gk is an eigenvector of q. So using that property of gamma k, we can prove the first convergence result on sequence generated by steep descent method. So let xk be a sequence resulting from a gradient algorithm that xk plus equal to xk minus alpha k gk, and let gamma k be defined as in the earlier lemma, and suppose that gamma k is positive for every k. Then xk converges to x star for any initial x naught if and only if sigma gamma k is infinity, means the series made of the sequence gamma k is not summable, right? So this is necessary and sufficient condition for the convergence of sequence xk to the optimum value x star. And for further analysis, we require this Rayleigh inequality, and that tells us that if Q is a positive definite matrix and lambda minimum is the minimum value of the eigenvalue of this matrix, then this relationship will be always satisfied. Lambda minimum Q into norm of x square will be less than equal to x transpose Qx, and this will be less than equal to lambda maximum Q into norm of x square, right? And there will be relationship between minimum eigenvalue of Q inverse and maximum eigenvalue of Q, and this will be given by lambda minimum of Q inverse equal to 1 upon lambda maximum of Q. And again, lambda maximum of Q inverse will be given by 1 upon lambda minimum of Q. And using this property of lambda minimum and maximum of Q inverse, we have this relationship. Lambda minimum Q inverse into norm of x square will be less than equal to x transpose Q inverse x is less than equal to lambda maximum Q inverse into norm of x square. Right, and using the above Rayleigh inequality, we have this relationship that if Q is a positive definite matrix, then for any x in Rn, lambda minimum Q upon lambda maximum Q will be less than equal to x transpose x square upon x transpose Qx into x transpose Q inverse x, and that will be bounded by lambda maximum Q upon lambda minimum Q. And we can prove this inequality by using the Rayleigh inequality. So here we see that x transpose. So if you consider this one, x transpose x square upon x transpose Qx into x transpose Q inverse x, this will be less than equal to norm of x to the power 4 upon lambda minimum Q into norm of x square into lambda minimum Q inverse into norm of x square. And so if norm of x to the power 4 will be cancelled, so this will be equal to 1 upon lambda minimum Q into lambda minimum Q inverse, and lambda minimum Q inverse can be written as lambda maximum Q upon lambda minimum Q. Similarly, we can show that x transpose x square upon x transpose Qx into x transpose Q inverse will be always bounded below by lambda minimum Q upon lambda maximum Q. So that inequality will be true in case of partial definite matrices, right? And now we can prove that if we have the steeper descent algorithm, then xk converges to x star for any x naught, right? So this is one of the very interesting property of steeper descent method, that it does not depend on the initialization, right? You can start from any point x naught and you reach to the optimum in a certain number of steps, right? Although you will see that it does not tell you, because in worst case it will give you the linear convergence. Yeah, but this is a global optimization technique. This is a globally convergent algorithm because you can start from any point x naught. So you will see that if we apply the Newton method, then Newton method's convergence rate is very faster. But the problem with the Newton method is that this is not globally convergent. If you start any point x naught, which is away from your optimum point, then there is no guarantee that it will converge, right? But in the case of a steeper descent method, and that is the region that this is applied everywhere, right? Whether you are doing machine learning, deep learning, and wherever you do, you will see that the stipend decision will come into the picture, because this will provide you the convergence, right? Is sequence generated by stipend decision method that will converge for any initial point x0. So you don't have to bother about the initialization. You can start from anywhere, and if you apply this method, you will get the optimum value for quadratic function. So if you see that if gk is 0, means gradient is 0 at the point xk, it means that you reach to the optimum, that is xk equal to x star, right? And so suppose that gk is not 0, means you have not reached to the optimum. Then in that case, your step length alpha k will be given by this formula. Alpha k will be equal to gk transpose gk upon gk transpose qgk. And if you put this value of alpha k into the expression for gamma k will be equal to gk transpose gk square upon gk transpose qgk into gk transpose q inverse gk. And if you use the earlier lemma and the property that gamma k is positive, we can, using the previous lemma 2, we can just prove that gamma k is greater than or equal to lambda minimum q upon lambda maximum q, and that because q is a positive definite matrix, minimum eigenvalue and maximum eigenvalue, though they both will be positive and their ratio will be positive. So what we get? We get that for every k, gamma k is positive, right? For every k, gamma is positive, right? It means that this series sigma gamma k, that will not converge. It means that this is not summable. So sigma gamma k will be infinity, right? It means that we can apply the earlier result that tells you that xk converges to x star if sigma gamma k is infinity. So since sigma gamma k is infinity, and that is necessary and sufficient condition for convergence of xk to x star, we get that our sequence generated by steeped descent algorithm will converge. And for any initial x0, because you see that this is not going to dependent on x0, right? So far we have discussed the steep descent method, where step length was, we are at each step we are optimizing the step length, and we are getting is as arg minimum of alpha for fxk minus alpha k gk, right? Or alpha k gradient of xk. But because you see that at each step we have to do the computation of the step length, right? And we have to solve a optimum problem at each step, right? So that is computationally very expensive. So then people try to just get the understand the convergence of this method when step length is fixed, right? So this step length here is alpha. This is fixed step length, right? And at each iteration you don't have to calculate the optimum value of the step length. Why? Because each time we have to do the solve a optimization problem to get the this alpha. So if we fix alpha, means alpha k is alpha for every iteration k, then our steep descent algorithm become like this: xk plus 1 equal to xk minus alpha gk, right? And if you just apply this one, we will see that how in what condition, right? Because this that earlier we know that if alpha is very big, number of iteration will be less, but there is a problem. Problem is that we can have require a zigzag type of moment, right? And if alpha is very small, then number of steps will increase. So what we wanted a alpha which is optimal, and that's why we applied the steep descent method. And but that each station we have to just get the value of alpha. So if you want to fix alpha, we'll see that what will be the bound for alpha to provide us the convergence. So we'll see that we will prove that if we have a quadratic function f, and if alpha lies between 0 and 2 upon lambda maximum q, if alpha lies between 0 and 2 upon lambda maximum q, then the steeper descent algorithm is globally convergent. For any x0, x will converge to x star, right? So if step length alpha is lying between 0 and upon 2 lambda maximum q, means divide 2 by maximum eigenvalue of q, right? And if alpha is less than this value and bigger than 0, then this fixed step size gradient algorithm will give us the global convergence. So, and we can just see it here that suppose consider this function, this quadratic function x transpose qx plus x transpose b plus c, right? So here this is our matrix q, but this is not a symmetric. So what we can do, we can just replace this matrix by a symmetric matrix of this form, right? So what we do, we replace it A by A plus A. Suppose this matrix is A. So what we can do, we can replace this A by A plus A transpose by 2. So this expression can be written in this form. And here we see that our matrix A now becomes a symmetric matrix. This matrix A 2 under root 2 upon 2 under root 10. This becomes a symmetric matrix. So now this expression Fx can be written like this, right? And we have to check whether our method converges or not. So because you see that this is a positive definite matrix, so value of alpha can be determined. So alpha, we see that eigenvalues of this matrix 8, 2 under root 2 and 2 under root 10, its eigenvalues are 6 and 12, right? So we have to find alpha k which is less than 2 upon lambda maximum q. So alpha must be taken less than 2 upon 12 and bigger than 0. So if alpha lies between 0 and 1 by 6, we can ensure the global convergence for this quadratic function applied to the steeper descent method, right? And we can see that relationship will be also true if we have a steeper descent method, that vxk plus 1 is less than equal to lambda maximum q minus lambda minimum q upon lambda maximum q into vxk. And using the earlier lemma 1 and lemma 2, we can prove this one. So we know that our gamma k is this expression. We have this expression for gamma k. Gamma k is this one. Gamma k is gk transpose gk square upon gk transpose q gk upon gk transpose q inverse gk. So if we apply this inequality over replacing x by gk, then we will get this one. Then gamma k will be bigger than lambda minimum q upon lambda maximum q. And gamma k is what? Gamma k is 1 minus vxk plus 1 upon vxk. So what we get? We get that vxk minus vxk plus 1 upon vxk is equal to gamma k, and that is bigger than lambda minimum q upon lambda maximum q, right? And you know that so what we get from here, we get that our gamma k is going to be bigger than lambda minimum q upon lambda maximum q. So gamma k will be either 1 or bigger than so lambda minimum q is always less than or equal to lambda maximum q. So this relationship, that you see that our whole convergence and everything is going to dependent on gamma k, and gamma k in case of quadratic function is dependent on lambda minimum q and lambda maximum q, right? So if we just denote this ratio lambda maximum q upon lambda minimum q by r, right? So this will be equal to norm of q into norm of q inverse, and this is called the condition number of q. This r, which is ratio of lambda maximum q upon lambda minimum q, is called the condition number of q. And if you apply the earlier theorem, which have a relationship between vxk and vxk plus 1, we can have this relationship that vxk plus 1 is less than equal to 1 minus 1 by r into vxk. So what do we see? We see that this relationship between vxk plus 1 and vxk is dependent on 1 minus 1 by r. So where r is the condition number. So 1 minus 1 by r plays an important role in convergence of vxk to 0, and hence xk to x star. So we see that so this 1 minus 1 by is called the convergence ratio, and if this is small, right? If you have the small value of 1 minus 1 by r, the smaller vxk will be related to vxk, because this is vxk plus 1 upon vxk is always bounded by 1 minus 1 by r. So if this 1 minus 1 by r is small, then vxk plus 1 upon vxk will be also small, right? It means that vxk converges to 0 faster in comparison to other cases, right? So this convergence ratio 1 minus 1 by r decreases and r decreases, right? And if r is 1, then lambda maximum q and lambda minimum q will be same. And in this case, the algorithm converges in a single step to the minimizer. And as r increases, the speed of convergence of vxk and hence of xk decreases. Because if r increase, 1 upon 1 by r increase, minus 1 by r will decrease, and 1 minus 1 by 1 will increase. So if this value is bigger, convergence ratio is bigger, then convergence will be slow. right? So how we define the order of convergence? Because you see that we have different algorithm for which we are going to get the sequence of iterates xk. So which method is suitable for us? It dependent on the order of convergence of the method. So we say that any sequence generated by a numerical technique xk that converges to x star, right? Converges to x star means limit of norm of xk minus x star is 0 when k tends to infinity. Then we say that this has the order of convergence p, where p is a real number if limit of norm of xk plus 1 minus x star upon xk minus x star to the power p is bigger than 0 and less than infinity, right? And if for all p positive, this limit is 0. Then we say that order of convergence is infinity. If this is 0, if for all p positive, this limit is 0, then order of convergence is infinity. And the order of convergence of a sequence is a measure of the rate of convergence. The higher the order, the faster the convergence. And if p is 1, then convergence is linear. And if p is 2, then convergence is quadratic. So we'll see that in case of steeper descent method, in worst case, we have linear convergence. It means that order of convergence should be 1. We'll prove that one. So just consider a sequence xk equal to 1 by k. And let us check that what is this order of convergence. So we see that 1 by k will converge to 0. So xk converges to x star is 0. So now get this ratio xk plus 1 minus x star upon xk minus x star. So this will be like xk plus 1 upon xk to the power p. So this is 1 upon k plus 1 upon 1 upon k to the power p, and this is k to the power p upon k plus 1. So if p is 1 less than 1, the above sequence converges to 0. If p is greater than 1, it goes to infinity. And if p is 1, the sequence converges to 1, right? So therefore what we get, because we wanted 0, we wanted this limit should be 0. This limit should be 0. If this limit is 0, then convergence is p. So here you see that for p equal to 1, for p less than 1, the above sequence converges to 0, right? Whereas if p is greater than 1, it goes to infinity, and p is 1, sequence converges to 1. Hence the order of convergence is 1. And just consider another case where xk equal to gamma to the power k, where gamma is something between 0 and 1. And if xk tends to 0, we can see that xk tends to 0, then and get the ratio xk plus 1 upon xk to the power p. This is gamma to the power k plus 1 upon gamma to the power k plus 1 to the power into p. And this becomes gamma to the power k plus 1 minus kp. And this is gamma to the power k into 1 minus p plus 1. So we see that p is less than 1, the sequence converges to 0. And if p is bigger than 1, it goes to infinity. But if p is 1, the sequence converges to gamma, right? And the order of convergence is 1 here as well, right? Because here what we wanted that this limit of xk plus 1 minus x star upon norm of xk minus x star to the power p, that should be a finite number. That should be between 0 and infinity. And we can consider other sequences and check the order of convergence. And we have also very important relationship that is about if xk be a sequence that converges to x star, right? So if xk plus 1 minus xk norm, x star norm is equal to big O of xk minus x star to the power p, then order of convergence will be at least p, right? And big O means that if we write that fs equal to big O of gx, then norm of fx upon mod of gx should be bounded in the neighborhood of 0, right? So this can be proved because we are given that, so we have to just prove that order of convergence at least p, right? Order of convergence at least p. So if order of S is the order of convergence of xk, then norm of xk plus 1 star will be equal to big O of xk minus x star to the power p, right? It means that there is some number c such that for sufficiently large k, norm of xk plus 1 minus x star upon xk minus x star to the power p will be less than equal to c. And then we can also see that norm of xk plus 1 minus x star upon norm of xk minus x star to the power s, that would be less than equal to c into xk minus x star into to the power p over p minus s. And then after simplifying, we can see that because this order of convergence is big, by this is order of convergence, then this will be something bigger than 0 but less than infinity. If you use that one, then limit of x star to the power s should be positive. right? Therefore, limit k tending to x star is 0. So what we get? We get that s must be bigger than or equal to p. So therefore, order of convergence at least p. So if this condition is satisfied, then order of convergence at least p. And we can see that if you have a function like that, x square minus s cube by 3, and if you use this algorithm, that steeper descent algorithm, and with fixed step length alpha. So xk plus 1 equal to xk minus alpha, a prime xk plus 1, a prime xk, and if you just have fixed step length alpha equal to 1 by 2, and initial x not equal to 1. So our f prime x derivative of f would be 2x minus x square, and xk plus 1 will be equal to xk minus alpha f prime xk, and this will be 1 by 2 xk square, right? So if we start with the point x not equal to 1, we can see that xk will be equal to 1 upon 2 to the power 2 to the power k minus 1. And if you just go for this ratio, sk plus 1 minus x star upon xk minus x star to the power p, we see that in case of taking p equal to 2, we get 1 by 2. This is finite. So convergence of this sequence is 2, right? So steeper descent may have, convergence better than 1, like 2 as well as in this case. But what will be its behavior in the worst case? So we'll see that in the worst case, its convergence will be linear. So to prove that, we require this lemma that in the steeper descent algorithm, if gk is not 0 for every k, then gamma k is 1 if and only if gk is an eigenvector of q, and we can prove it. So we recall that gamma k is given by gk transpose gk square upon gk transpose q gk into gk transpose q inverse gk, and it's sufficient. It is easy to prove by verification that that if gamma k is 1, then we are done. So to show that this necessary part, we suppose that gamma k is 1, and then vxk plus 1 will be 0, and that will imply that xk plus 1 equal to x star, right? So therefore, if you write x star equal to xk minus alpha k gk, and if you multiply with q both sides, so we get that qx star equal to qxk minus alpha into qgk, and if you subtract b also, so you get qx star minus b equal to qxk minus b minus alpha k gk, and qx star minus b 0 because x star is the optimizer, and therefore q star is b. So left hand side is 0, and right hand side will be gk minus alpha k gk. So what we get? You get that q gk equal to 1 upon alpha k gk. It means that this gk is an eigenvector of q with eigenvalue 1 by alpha k. And then we have this final result that if the fk be a sequence generated by steeper descent algorithm applied to a function f, then the order of convergence of xk is 1 in the worst case. That is, there exists a function f and an initial condition x naught such that the order of convergence of xk is equal to 1, right? And we can just see that we have vxk is bigger than or equal to lambda minimum q upon 2, that is xk minus x star square, and combining the above inequalities, we can just check that xk plus 1 minus x star will be bigger than 1 under root 1 minus gamma k, lambda minimum q upon lambda maximum q, and norm of xk plus 1 x star, and therefore it is sufficient to choose that x naught such that gamma k less than d, and then we are done. So gamma k will be given this value, and g naught is also an eigenvector of q. And by using this one, we can just show that gk equal to xk plus or minus xk upon alpha k is not an eigenvector of q for any k. And because any two eigenvector correspond to lambda maximum and lambda minimum, they are mutually orthogonal, right? So, and also gk lies in one of the two mutually orthogonal directions. Therefore, for each k, the value of gamma k is one of the two numbers, both of which are strictly less than 1. So this proves that the case when we have two directions. And if we have general n case, so let v1 and v2 be mutually orthogonal eigenvector correspond to lambda maximum q and lambda minimum q. And if we choose x naught such that x naught star is not 0, lies in the span of v1 and v2, but is not equal to either, then we can write g naught equal to q into x naught minus x star, and this will also lie in the span of v1 and v2, but is not equal to either. So by just using some simple matrix property, you can write that xk plus 1 equal to xk minus alpha k gk, and then we can write gk plus 1 equal to I minus alpha k q gk, right? So any eigenvector of q is also an eigenvector of I minus alpha k q g. and therefore GK lies in span of V1 and V2 for all K. That is, the sequence GK is confined within the two-dimensional subspace spanned by V1 and V2, right? So it means that we can reduce this case to the case of n equal to 2, and for n equal to 2, we have already proved that we have a convergence. So that was all about different properties of steeper descent method. For more deeper understanding, I will recommend a book that we wrote in 2014, and then there is another book that is by EKP Chong and H. Jack, Introduction to Optimization. Another very nice book is Convex Optimization. Anyone interested may go through that book, right? So these are some important references for anyone who is interested for further study about steeper descent method and another algorithm. So with that, I would like to conclude. Thank you very much. These are some references. Thank you.
Thank you so much, sir, for an informative session. I'm pretty sure the precious knowledge you have gave us will definitely help us. Now the session is open for question and answer.
Yeah, please.
Hello, good afternoon.
Yeah, afternoon. Yeah, please.
Yeah, it was an amazing session.
Thank you.
I have a small question
Yeah, please. Yeah.
regarding um, the manner of convergence. So we talked about the order of convergence,
Yeah,
but is the manner of convergence like a monotone convergence, or like it sometimes converges, then at certain values of p it might diverge, and then again it converges again? So I
No,
mean,
no, no, I tell you.
I don't know whether I'm being able to frame the question properly, but
Yeah, I got your point. Actually, you see that because if you just apply steeper descent method in each iteration, like if you go from xk to xk plus 1, value will decrease. This is one of the most essential property that I have proved here, that if we apply steeper descent method, we will get descent. So at each iteration, there will be always at least a small improvement in the value of the function, right? So there is no point that it will increase. This can never increase. This has to decrease. But the important point is that in what ratio, right? And for that we have required this order of convergence. So in worst case, we have proved that this will give you a linear convergence, right? But when we apply Newton method, or when you apply conjugate direction method, so for conjugate direction method we have quadratic convergence, right? So this is better convergence in comparison to our steeper descent method. The problem is with conjugate direction is that we have to find the conjugate direction first, and if you go to the conjugate gradient, we again require more information. And if you want better order of convergence, like Newton method, then again we require more information. Like as we see that in case of Newton method, what we require that our direction will be given by minus inverse of the Hessian multiplied with the gradient. So we'll get better convergence. And even for quadratic function, because all the time with Newton method, we are going to approximate the function. We quadratically approximate the function. So that's why for quadratic function, we have a global convergence there, and we get the optimum just one step, right? So for quadratic function, that is better, because we are getting global convergence and we are getting the our optimum point in just one step with Newton method. But for other function, this is not good. So each method have their own problem. But one thing that has been ensured is that at each iteration we get some descent. We get some decrease in the value of objective function. It means that we are moving in the direction of the optimum. But yeah, speed can be slow or more. So as I have seen that if we take a function like this, x square minus x something was there. Yeah. So here we see that our order convergence is 2. It is for this function. Fx equal to x square minus x cube by 3. If we take this function, right? So I have shown that order convergence 2 here. Right?
Right.
Yeah. But there are functions like I have shown you there in the beginning with the this one, that we are not getting the optimum in just 2-3 steps. We require more iteration. So that is, one problem with the steeper descent method, that you don't know in how many steps you get the optimum, right? And
Yeah.
one positive thing with conjugate direction is that if you have a quadratic function and if you apply conjugate direction method, you get the optimum just n step. If you have a quadratic function of n variable and you apply conjugate direction method, you get the optimum just n step. With Newton method, you get in one step. But with the steeper descent method, you don't know in how many steps. But yeah, but it will converge and it will give you the optimum if you run the program. For some case in few steps, and for some other case, you require more steps. So that is the point.
Sure, sure. Actually, it's a very wonderful algorithm. I did not know this before. I work with machine learning algorithms.
Yeah, yeah.
Where
Actually, in machine learning,
sometimes the loss function is like really erratic.
Yes,
And
yes.
other methods do not seem to converge. So
Yes.
since you were saying that this definitely converges, I think next time I train a machine, I would be using the steepest descent method
Yeah,
for
yeah.
that. Thank you so much.
Actually, that is the point that why I discussed it here, because this is going to applicable everywhere. And if you just just check it, right? Your machine learning algorithm, also in deep learning, you will see that this some sense it is going to be used. Maybe certain variant of steeper descent like stochastic gradient method or other version of steeper descent method will be using there, because this requires less information about the function, because you know that your function may have other problems like function may not be differentiable. Then in that case you can go for the subgradient descent method, right? And if like their probability distribution kind of thing is there, then you can have stochastic steeper descent method. But this method is there, sometime you use it in front and sometime it is hidden, but this is everywhere. Most of the time steeper descent method is used, because for other method we require more information and more well behaved function. Like for example, we apply Newton method, we require second order derivative, and which is not the case with many functions. So that's why this method is very popular, and very many variants of that method have been like introduced.
Yeah, thank you so much. I'm clear.
Thank you very much. Yeah.
On the behalf of MIT Madhya Pradesh, would like to thank you for giving your time to share your profound knowledge with us. Thank you so much, sir. Thank you everyone for joining the session.
Yeah, thank you very much again to you, ma'am, and to my old friend Ramkumar and your organizing team. Thank you very much, and keep organizing such program so that we can have that interaction. I like that one, and this is really going to be helpful to everyone. So thank you very much.
Thank you everyone. Kindly join the next session, which will be held tomorrow. Thank you everyone again.